So we are going to start.
We are going to start the afternoon session then. First, Professor Roeda will make an announcement.
Okay, this is just very fast because you arrived this message this morning. This is from the consulate of Italy, Bremen. Bremen. This is from the consulate of Italy in Bremen. So I will. It's in Italian, but I will translate it for you. Okay? This is So, dear Remo, I would like to wish you. Also, on behalf of Ariana Pascoli and Marco Egger, my warmest wishes for your 8th birthday. I apologize not to be there in presence for this celebration, but I'm very happy that a representation from the scientific community of Bremen, Klaus Lammersal and Hansjoerg Dittus, are there with you to enjoy this event. So, Felix here. With them, also with the Senator Claudia Sheen, we are frequently in contact for the project of ICRANet at Bremen. And we hope to concretize this in the future, this important international project. Having said this, again, I wish you happy birthday. And I hope to meet you soon in person. Warmest regards, Marco Fuchs.
Okay, thank you very much, Jorge. And we are very proud that Marco Fuchs sent this letter to us. And we are now starting to the second session here of the day and the second day. The first talk today will be by somewhere here. Will be by Felix Mirabel from Argentina and from France, and he will talk about black holes in the early universe. So please, Felix, can you share your screen?
Yes, I'm trying.
We do not hear you.
Can you hear me?
No, your microphone is off.
Can you hear me?
Yes, yes.
Okay. Can you see my screen?
Yes.
Okay. Well,
so
thank you. Is that all right? Yes. Okay. Sorry.
You can see everything well.
Okay. Well, I want to remind that in January 1971, Remo published a long article in Science with Nobel Prize winner introducing the idea of black hole, and the discovery, and it was said in that paper in the introduction that the discovery of black holes will be of great significance for physics. And that was 50 years ago. Now, following this statement by Remo, excuse me, I have to get rid. Well, I have to know why. Well, can you see the title? I cannot see myself, but can you see the title, Black Holes in the Early Universe?
Yes, everything is good.
Okay. Well, so I will talk on the importance of black holes in the early universe for our understanding of one of the frontiers in cosmology. And the work I'm going to talk about is based on a very extensive new astronomy reviews that we just published last month in collaboration with Luis Felipe Rodriguez. And the idea is that here there is a schematic representation of what is nowadays our understanding of the evolution of the universe from the Big Bang up to the present age at 13.8 billion years. And what I'm going to talk is on the role of black holes in the in one of the frontiers of cosmology that is called the Era of Re-Ionization, when the universe changed from being essentially neutral to be the intergalactic medium, completely transparent, because it was almost fully ionized. And one of the important results since in the two last decades has been the discovery of 10 to the 9 solar masses supermassive black holes in quasars when the universe was less than 1 billion years old. And this is a important discovery that presents a challenge for us, because we don't know how these supermassive black holes with these masses of up to 10 to the 10 solar masses could have been built when the universe was so early. And the main conclusions so far in the community is that massive black holes are born before and grow faster than the stellar bulges that surround them in galaxies. And also we are coming to the realization that massive black holes, besides impeding star formation by the production of jets by the black holes, they might also trigger star formation when the gas densities were very large as in the early universe. And these discoveries have triggered again the idea that black holes could be an important component of dark matter. Now, quasars and radio galaxies, we know nowadays, host supermassive black holes that are sources of high energy radiation and relativistic jets that can reach distances of millions of light years. And these jets are wonderful laboratories for high energy physics. And we know this, or the current paradigm is that these relativistic jets are powered by the spin of the black holes on accretion disk and collimated by magnetic fields. We know now that stellar black holes produce also radiation of high energy, and also relativistic jets. Since the launch of the French Soviet space mission Granat for the observation of the gamma ray sources in the near universe, were identified sources that are stellar mass black holes that are at the center of two-sided jets that, instead of reaching distances of millions of light years, reach distances of a few light years, and also superluminal motions, apparent superluminal motions, were discovered using the Very Large Array of the National Radio Astronomy Observatory. And these ejections we know now that have apparent superluminal velocities, and that the kinetic energy of these plasma clouds that are ejected are enormous, are comparable to what would be 1/3 of the moon mass moving at 98% of the speed of light. Now, we know also from observations of galaxies, dwarf galaxies, that will be analogous to the first galaxies formed, namely dwarf irregular galaxies, very rich in gas, like this one, that is an example, at only 9 megaparsecs. It's a dwarf galaxy, irregular, very rich in gas, that caused a massive black hole that is indicated here by the radio emission in green, that triggered by jets, star formation at distances of about 70 parsecs, because these jets, by mechanical energy, compact the gas when it is very dense and triggers star formation, in this case at distances of 70 parsecs. Now, the fact that in this galaxy it is found a black hole with a mass of about 1 million solar masses without a stellar bulge is indicating that the black hole was formed before the possible stellar bulge that may be formed later on in the evolution of this galaxy. Now, we know, on the other hand, that in the local universe, there is a correlation between the black hole mass, shown here in the y-axis, and the mass of the central stellar bulge that is shown in the x-axis. It's with some dispersion, it's a very, over several orders of magnitude, it is observed. But when one goes to the black holes in the very early universe, when they were at redshifts greater than 6 up to 7, the masses of the black holes, of those black holes indicated here in color, as a function of the galaxy mass and bulge mass, which is the bulge mass is shown here in this straight line, comparable to this one. They are offset. So in the early universe, for a given stellar mass of the galaxy, in the bulge or total mass of the galaxy, these supermassive black holes are offset, so they have a excess of mass relative to the present universe. So this suggests that in the early universe, supermassive black holes come before and grow faster than the rest of the galaxies. Now, one of the questions and puzzles at present time is that it's not yet clear how these supermassive black holes with 10 to the 9 solar masses could have been formed in the universe when it was less than 7 million years old. And you can see here if one assumes that the black holes grow at the Eddington limit with a typical radiative efficiency of 10%, in this diagram, it is shown that the seeds of these black holes, when the universe had just 100 million years, should be black holes of intermediate mass, with masses in the range of 3 to 4 solar masses. In this diagram, what is shown is the mass of the black holes, of the 7 black holes with redshifts greater than 7 discovered so far, namely black holes which which are found when the universe had only less than 7 million years old. And this diagram, these lines, this is, sorry. And in the x-axis is shown the redshift, and on top the age of the universe. And these diagrams show that the seeds of those black holes at 100 solar masses should be black holes of intermediate mass. But the question is whether these intermediate mass black holes could grow, could have such a growth and be sustainable for 600 million years. And this brings the question, or triggers the questions of whether these supermassive black holes are of astrophysical or primordial origin, as Seldovich and Novikov proposed for first time, coming from the original plasma of the universe by some inhomogeneities in density. This is the first question that is not answered. And the second issue is that perhaps the majority of intermediate mass black holes in the early universe had a transient existence. So they come to existence under conditions where they cannot stop becoming supermassive black holes. And all of this could be due to the fact that the growth of massive black holes depends on the density of the gas, which in the early universe there should be between 1,000 and 10,000 times larger than in the present universe. So one important aspect of this very early black holes is that some of them are extremely radioluminous for their mass. So they offset, there is in general a correlation between the mass of the accreting black hole and the radio flux. But there are supermassive black holes at redshifts greater than 6 that are extremely luminous. And if that is the case, and if these supermassive black holes are the tip of an iceberg of black holes that are very radioluminous, also of smaller masses, there could be a synchrotron cosmic radio background, which presently is of unknown intensity. But this radioluminous, extremely radioluminous, 1,000 times that what is typical in radioluminous black holes in the local universe, they suggest that there should be a cosmic radio background of synchrotron characteristics. So, and the question that the community has asked is whether this cosmic radio background could be impressed as an absorption signal in the 21 centimeter line of H1. And this is why major radio astronomy observatories and experiments at low frequencies, the main science driver is the detection of this absorption signal in the hyperfine transition of the 21 centimeter line of atomic hydrogen. And the first tentative detection of this absorption was reported by an experiment called EDGES in the desert of Australia, in Western Australia. And you can see here the result they reported in Nature. The brightness temperature of this hyperfine transition as a function of redshifts and age of the universe. And in colors here are shown the absorption that would be expected of the cold atomic hydrogen against the cosmic microwave background, the cosmic thermal background. And EDGES reported an absorption amplitude that was very large compared with what was predicted against the cosmic microwave background. And to match this absorption, the cosmic radio background should be of the same order of the cosmic microwave background at those very early epochs, which is an enormous intensity. So in the work we did, we tried to match this absorption reported by EDGES with different astrophysical sources. For instance, black hole X-ray binaries like Cygnus X1, Cygnus X3 perhaps, and others. And we find that these sources are radio inefficient sources. And we explain why. So when we started to make our calculations, we were expecting that that X-ray binaries, black hole X-ray binaries, could make an important contribution. But we, making the calculations, we found that they could not match the EDGES absorption by 7 orders of magnitude. And then supermassive black holes in the local universe, like the one in Sagittarius A star, Centaurus A, M87, cannot also match the edge's amplitude of absorption, and neither ultraluminous infrared galaxies like up to 20. So we made all the calculations and concluded that only these supermassive black holes in the very universe, these radioluminous supermassive black holes in the early universe, could provide the flux to match the edge's absorption. And that at that time, in that case, more than 75% of the mass in stars at that epoch should be in black holes in order to match this absorption. Now, when our paper passed the referees and so forth, we appeared a paper at the end of February. This is a Indian experiment in a lake. It's a radiometer experiment. They concluded that they didn't match, they couldn't confirm the edges report, and that shows that the global observations, the global search for this absorption, expected absorption by single instruments are subject to systematic errors of difficult control and errors at the instrumental side and also the analysis of the data. And the expected signal, the problem is that the expected signal is about 3 orders of magnitude less than the galactic emission. The redshifted 21 centimeter line of atomic hydrogen, those redshifts of 20 correspond to approximately to frequencies of 70, 80 megahertz. And the own galaxy is producing a very strong program to detect these weak signals. So, but interferometers, like in the case of the cosmic microwave background analysis, interferometers like SKA are necessary to detect the H1 signals. And we are living in an exciting epoch because massive black holes and galaxies in the epoch of re-ionization may be detected very soon in direct way by the Webb telescope with the instrument MIRI, mid-infrared instrument on the telescope. And these massive black holes will be detected, is expected, up to a redshift of 15. We know now that the Webb telescope is working perfectly. That was communicated about 1 week ago by a press release. My colleagues that work on MIRI were very excited because it's working better than expected. And the other way, if one wants to go further away, up to redshifts of 30, there could be the indirect detection by observations of the redshifted 21 centimeter line of atomic hydrogen with interferometers with SKA or perhaps with future low-frequency radio observatories that are planned to be installed on the hidden side of the moon. So this large review that has addressed many questions besides this that I presented today is already published in this reference. Thank you very much, and Remo, happy birthday, Remo, and good continuation.
Okay, thank you very much. Also, thank you for keeping perfect in time. Other questions? Yeah, I will. Other questions in the audience here in Gnss? Other questions online?
How can you, Felix, thank you for the very nice talk. How can you expect what will be the origin of primordial 10 to the 3 to 10 to the 4 solar masses black hole? Do you have any idea of how to produce them?
I couldn't hear very well the question. I know I hear that is on the origin of the intermediate mass black holes.
Yeah, how can you suggest origin of such objects of 10 to the 3, 10 to the 4 solar masses, primordial origin? Is there any favorite mechanism that you have?
Well, there are two ways. One could be primordial in the original plasma, very early in the universe. There could be inhomogeneities as in the cosmic microwave background on this plasma that will have in the density that will grow. This is an idea that on which there are a lot of publications, mostly in physics journals. Now, astrophysicists in general think that stars are formed in groups, and perhaps and will be because of the low metallicity relatively massive, up to 100 solar masses, and these stars will merge and form this and these very massive stars collapse and form black holes of intermediate mass very early in the universe. These are the lines of. I think we will solve this question that you formulated very soon with the web, because the web will show how was the rate of these supermassive black holes, of growth of these supermassive black holes from redshift 15 up to redshifts of 6 or 7. And this will tell us the signatures of if these very supermassive black holes that have masses equivalent to the masses of the most massive black holes in the local universe, how they grow. And from there we can, the mechanism of growing. And this will tell us something about if they are of primordial or astrophysical origin.
Okay, thank you very much for this answer. I don't see more questions. Then thank you very much, Felix, for the nice presentation. Yeah. And we continue with the talk of Giovanni Lamanna from Gnss. And
Just a moment, I will
yeah, yeah.
upload one.
So Giovanni Lamanna will speak about open data and open science in astrophysics, a very actual topic today.
Klaus, I managed to connect again. Now I am connected, Klaus. Tira qua. Hello?
Just fixing the presentation, so please be patient for a moment.
Appena finito Mirabel.
Parla, vedi se ti sentono per concludere.
Hello? Can you hear me? Klaus, can you hear me?
Felix, I think you should stop sharing.
Orge, puoi sentirmi? Orge, potete sentirmi?
Ti sentiamo tutti, Remo.
Bene. Mi sono appena riconnesso. Sì.
Quella che pulisce, li vede.
Vedono, non te lo fa vedere più.
Non fa vedere questa.
Ah, no, no, lo so. Lo so.
Questa gliela porto, l'ha chiesto.
Ridagliela.
Ok.
Come faccio? È in ordine adesso.
Oh, perfetto. Non si stacca più. È sempre attivo. Metti, consumerà molta batteria il telefono.
Conviene tenerlo attaccato.
Sì.
Ok.
Quando torna, portami delle mutande.
Sì.
Oh, yes. Ce l'ho chiesto. Ce l'avevo chiesto ieri.
What is going on? Aspetta, dove sono io?
Qua.
No, ho capito, ma dove sono? Ah, ecco qua.
È attivo.
What is the problem?
So it will start in a minute. Shortly.
Spostare la macchina. La macchina è messa molto male.
Va bene, non credo che ci sia altro.
Bravo.
Sì,
Per favore. Va bene?
va bene.
Funziona.
Sì.
Ci vediamo dopo.
Sì, dovresti dire al coso che venga a trovarmi.
Oh, beh, papà, vediamo tra un po'. Ti porto.
Sì.
Ok.
Aspetta un momento.
ce l'hai?
No, mi metto
Perché?
le scarpe.
Perché?
Beh, perché se viene qualcuno voglio...
Non adesso.
Sì, ma fa poco.
Ti chiamo,
Pascal.
ti chiamo prima, veniamo insieme.
Ah, va bene.
Ok.
Con Pascal.
Sì.
Sì.
Okay.
E anche...
Okay, so thanks a lot. Let me just start wishing all the best to Remo for his 80th birthday. I'm honored of his invitation here. I'm not going to tell a story of research conducting together because I'm a little younger than him, but I know that Remo wanted me to talk what I'm doing about open science because it could fit with his perspective concerning ICRANet for the future. But anyhow, I take the opportunity to address my message also to Remo, all my grateful for his friendship. I'm always admirative for his outstanding contributions to physics, also constantly inspired to discuss about networking, training schemes, and constantly looking at the future together. So thank you, Remo.
Thank you.
So the talk will be about ESCAPE. ESCAPE is the European Science Cluster of Astronomy and Particle Physics Pre-Research Infrastructures. The title that I choose is more from open data to open research, talking about new paradigms, challenges, and opportunities. And allow me to say that I will give you a little of elements of background, elements concerning the project, and an outlook to the future. So you will have also something about science to a certain point, but you will see that I hope this will trigger also discussions and future brainstorming for future plans. So the very first preamble is to talk about, or at least mention to you, that European Open Science Hub exists today. That was originally a European Commission action or a principle, a project, which anyhow was in response of the Union member states' shared policy about open science. Everything conducted, as you know, by the European Commission is coming top-down from the member states, from the governments. And in principle, the idea was that EOSC should be the cloud for research data in Europe, allowing universal access to digital objects through a single online platform. That in its own architecture should federate existing national resources and allowing both researchers as well as fellow citizens to access and reproduce the scientific results. Now, when you move these concepts in reality, you have to consider that there is an important heterogeneity among the different domains, scientific domain, and also different skills and background from the different scientific community. Therefore, the implementation by itself as a unique architecture is something quite complex. What happened is that since July 2020, now we have a legal entity, which is called the EOSC Association, to which a lot of universities and research institutes that participate are member of, and you can find link here. Now, open science. Open science, you know, that has become a pillar of the current national and international views and political programs of governments, research funding bodies, and forums. Now, when we talk open science, some years ago, we talked about the free access to the publication without any charge. Well, this was the point of the peak of the iceberg, because indeed is much more than this. Today, and this is my own favorite choice, there are behind open science three main ambitions. Change the way citizens could perceive research and public investment for research, and this is high in priority today. Enable opportunities offered by the digital revolution to allow everybody to participate in the scientific process. And when I say everybody, this should recall all of you the citizen science, the participation of citizens in the science challenge, the scientific challenge, but also, and this is important for all of us, for our communities, we have to believe that this could accelerate the discoveries and increase the scientific value by sharing data, transferring knowledge within scientific communities. Sharing, networking are the key words for that. And from open science, we now move to open data. And when we talk about open data, we do not talk about free data. Because depending on what data are or who are producing these data, there are conditions governing their access and reuse. Therefore, we cannot talk about free data. When we talk about open data, we actually talk about fair data. The fairness means that the data are findable, accessible, interoperable, and reusable. And data are any digital object associated to scientific discoveries. Now, let's come to ESCAPE. In 2018 and 2019, there was a specific action called the Nature 2020 work program, called Connecting S3 Infrastructures through Cluster Project. So S3, you probably know, is the board representative from the governments that lists in many different domains those projects which are priority projects for the European member states. And through this action, the governments, they wanted the Commission to force a commitment from the legal entities managing the projects, and in our domain are the observatories, the big science projects. And there are 5 domain-based clusters, apart ESCAPE for particle physics, astronomy, and nuclear physics. There are also the environmental science one, there is the EOSCLIFE for biomedical science, PANOSC for neutral light sources facilities, and SHOCK for social science and humanities. So you see that more or less the expected impact from these cluster projects, which altogether cover more than 80% of the SP projects, were actually based on cross-fertilization through large scientific communities and applying the standards, economy of scale, but in principle, trying to push the community to the implication of the fairness of data, and then, of course, linking those projects to the concept of the European member states of the EOSC. In this picture, you see the projects that are that are encompassed within ESCAPE. So you have FAIR GSI for nuclear physics, you have the high luminosity LHC and the other CERN infrastructures for particle physics. And then the bulk of the others are CTA for gamma ray, high energy gamma ray astrophysics. You have Virgo Ego for the gravitational waves. You have ESO for the ELT and its own other telescopes. You have the European Solar Telescope, the Giant ERIC, that is a network of radio telescopes, ChemTriNet for neutrinos, NSST Vera Rubin Observatory for the optical telescope in Chile, and then SKA, that is next generation radio observatory. Why we came together? There was an analysis in 2018 considering the following 5 bullet points. First of all, that there were already some complementary excellences in data stewardship. You probably know, because you have been using those data, the astronomy community has already quite a culture in data stewardship with the virtual observatory infrastructure. And the particle nuclear physics about the management of large data size, data volume, large scale distributed computing. There were already synergies because it happened that a lot of national institutes and research agencies were covering and supported a good fraction altogether of these projects that are partners in ESCAPE. All these new generation projects, most of them together, are representing the generators of exascale data volumes for our communities. New generation of experiments are moving in the operational way of facilities, open facilities of observatories. Therefore, there is really the need of curate data, of guaranteeing the open access and the sustainability. And then we were obviously as a community concerned by connecting the ES3 to EOSC, transforming such original concept in something that is corresponding to communities. So this is a nutshell, the partners. We are entering the last semester of the H2020 projects, but you will see that there is a long-term path for all 5 clusters that are finally well acknowledged in Europe for their contributions. So I will not give you the details of the technical developments that are in the project, but I try to explain you how we are tackling the question of the open science. First of all, together we develop one work package that is about data lake. We want to build, and we are building, a scalable federated data infrastructure where we have all data, where the users can select the data sets and analyze the data sets and combine. When we talk about data sets, we do not talk exclusively about this data coming from the observatories, but also all the digital objects produced by theorists with their Monte Carlo simulations, with their phenomenological studies. This is, let's say, the legacy of our community. Then we need also to build up scientific platforms for allowing the researchers to perform the data analysis, as well as customize them to the specific need of the specific observatory. And then there are the interfaces. One is the typical in astronomy, is the virtual observatory that has to scale up to the new challenges of the new projects. And then a repository, a sort of archive of all software, of our know-how, all the simulations, all the wonderful works that we have seen during these days in the different talks deserve to be part of our community heritage through such a catalog, which is going to be sustained in the future. And then also a sort of citizen science, an approach to provide citizens the access to this science. When you bring these packages and these works, you build up our architecture that we call the EOSC cell. This is our way to produce this. So you recognize that there is the interface of the data infrastructure, which also interfaces with the heterogeneous computing and the GEMT, the connection among the states and the observatories. On the left-hand side, you have the catalog and the repository of the resources, which also include actions for training and innovation in the workflows, software, artificial intelligence, quantum computing, whatever you can figure out, and we are supporting. And then on the top, you have the different way you do access or you customize the access to the researchers, to the resources. So what's happening now? That the way the EOSC cell that I depicted to you has expected to have an impact is because at the end is going by discipline to participate in the deployment of a sort of EOSC web of fair data and services for science. And what we use to now call it such an approach is a virtual research environment, because we want to, and we are deploying a prototype of really web-based environment where a single researcher is able to identify him or herself, to have access to the catalogs, to also run his workflows, explore an analysis which already has been matter of the publication, reproduce such analysis because it has all the digital objects connected to these results, also produce new results, publish it, and also rewarding the scientists that are committing in such an open science environment. I want to bring your attention to the few lines that you have here that I can guarantee that corresponds exactly to one of the next policies that are applied by in Europe, and where networking like ours in our communities is expected to have a role and to produce something. The idea is that we need also to evolve the practices in the assessment of research, giving increasing value to open science contribution with all a wide range of digital objects attached to publications, but also investigating and putting in place some open peer reviews for the traceability and coherent comprehensive metrics of all these fairness data. So it's really a change in the way we produce and we publish our results. Therefore, this environment then you can also figure out is corresponding to the next generation researchers that are more used to stay in electronic environment, including the social network. Exactly this is a social network of science, including the possibility to reproduce scientific results and produce new results on top of those that are published, rewarding scientists for their commitment. Now, this VRE is hosting the test science project. This was a concept which, as a reminder, is aligned with the third pillar that I presented to you about open science, accelerating discoveries. Was a principle, was an idea in ESCAPE to validate at the end the different technical developments and implementation of the VRE. The other four clusters, including the Commission, accepted this idea that was coming from us to make it a sort of explorative pilot to enhance the research, the participation of researchers in such an endeavor. So we got a second funding with the EOSCO Future project with the cluster together, and we have produced, we are supporting now a bunch of postdocs working on this test science project. And this is done also in cooperation with ECFA, NUPEC, APEC. So those are the consortia of national institutes in nuclear physics, in accelerator physics, in astroparticle physics. There is also ASTRONET for the, and RADioNet for the astrophysics. And such test benches are therefore aligned with the initiative of those consortia, national institutes working together, therefore with a sort of let's say, internal investigation and also external survey. We decided for this stage to focus on largely the dark matter search as a test science project and the extreme universe. Within each of these two thematics, we have pilots, and the postdocs are working in these pilots with the following approach. First of all, they bring their own recent publication in such a virtual research environment. And then they start a new analysis, new research, original one, that will bring to a publication, including the all digital objects for reproducibility of their results in the VRE. So this is happening, for instance, I'll give you some some examples. This is coming around dark matter in a transversal way. Those are example of, these posts are example of a combination of indirect of research of dark matter candidates at the accelerator with the data from the LHC experiments. We have another pilot on the indirect dark matter search with neutrinos and gamma rays, where we have been combining the data from different observatories. Researchers have produced also new workflows for reducing the background, increasing the statistical combination of the signals, and try to publish actually competitive exclusion lines in the cross section of the dark matter candidates aniquilating in cosmic rays. So all these works will provide researchers to combine and interoperate data. As an example, going to exclusion plots where they have in the phase of space all data coming from the different experiments. If we move now, so yes, here we are still in the dark matter. This is another example where, without entering into the technicalities, we see how, from one point of view, there are original works in progress exploring a specific channel for the research of dark matter with the Z boson mediator at LHC in Atlas. But in the same time, as you see on the bottom, you have also the choice of all the technical services that are open source to sustain the environment, the software, and this is commonly done, whatever is coming from particle physics or astrophysics, in order to guarantee that we adopt the same services and we build customize on the requirements of the scientists, such a virtual research environment. When we move to the extreme universe science projects, since it is quite large and we were based on suggestion from scientists, we had compact objects or gamma ray burst, or even again fundamental physics with cosmic messengers, centered on different research infrastructure. In one case, through the radio telescopes with the low far legacy data they want to reanalyze the raw data, or in other case, combining the data from CTA, Virgo, ICRANet, SK, and others. And in the third case, for the question of by using the gravitational waves as a potential signature for dark matter. With all these approaches, we have something which is really innovating in terms of, for instance, as it is this case of machine learning applied to the evidence of gravitational waves glitches in the data from Virgo, as well as in trying to implementing a sort of software and services structure that is conceived for offline data analysis. But now we are investigating the way to transfer this in the low latency multi-wavelength combination of data. That is really another challenge. Or even for the perspective of the telescope, the third generation interferometer for gravitational waves, exploring how through simulation and methodological studies we can also using gravitational waves as messages for fundamental physics. So these are examples, and as we have been discussing a long time with Remo, a lot of works that have been done, for instance, Pascal, by students in Era initiatives, those works deserve to be considered in such an environment because they represent the latest, and also new PhD students can work in such an environment and be rewarded for their work. Again, in Astroparticle, we also interface with the archives of the Virtual Observatory, and here again we are working together with ISO and ESA because they also exploit the Virtual Observatory for their own open data portals, and the Virtual Observatory needs a sort of evolution to be aligned with the large volume of data and also the combination of data which will not be based exclusively on spectral measurements or image, because there are also signal-based like gravitational waves interferometer observatories. Or when we talk about the software, the catalog, there is a lot of innovation, as I said before, but also including for the next generation astronomical experiments, all those open source software that are, let's say, the results of a foundation approach, large community working on this open source software, which will be the software for the analysis for the workflow of gamma rays or the radio, is the case of gamma pi respectively and CASA. And the same as I said before, by combining the multi-messenger data analysis practice with new services and new software. One more example, we have a publication of through this action of using the cross-fertilization, the cross-know-how about machine learning, or deep learning, how to apply the deep learning to some archive data to infer stellar parameter just by looking at large number of spectra in an automatic way. This is a publication coming also from colleagues from ISO. Now, I come back to the political aspects just to remind you that the clusters are working together by publishing position statement. And the last one that are accessible here, you will see that they also are proposing themselves for the future to give continuation to this action. And in these terms, we have a dedicated workshop with the stakeholders showing how the clusters are, the science clusters are playing a role and becoming actually platforms, collaboration for the future further than the duration of the current H2020 grant. And indeed, what's happening is that we have now collected the signature of the core ARISE partner escape for a new open collaboration agreement which will support the action for the next years, and in particular in the framework of Horizon Europe. This is an open collaboration. In principle, will be open also to other projects. And the way we are moving is to consider the legal entities operating those research infrastructures as a partner, because automatically we guarantee in such a way the inclusiveness of all the university, all the institutes that are supporting this project and are supposed to exploit those data to progress to do their research. And this is what the governance, this is what the European Commission is asking, the large inclusiveness. And in this respect, we have, and we come to my conclusion is that we had ahead of us important opportunities. That is a consequence of the success story that I try in a few slides to tell you. Open data and open research are changing the paradigm, and in my opinion, are improving the way we perform research, at least in the way we build the heritage of what we do for the next generations. The domain-based science clusters are expected to be largely inclusively, and I can add here that in the next framework, what is expected is that we were able to also support initiatives of networking of universities, of institutes, or competence centers like ICRANet, or furthermore enhancing synergies among phenomenological studies and analysis of astrophysical observation. In our test science project, we have also theorists working on all the subjects that I have shown to you, and are already in the VRE prototype providing access to all their simulators. They have also the possibility to interface the HPC platform that you use to exploit for your calculation. And a future evolution of the scientific program of ICRANet can be also considered in this context. And probably an opportunity for make fair the legacy scientific achievements of Remo and the ICRANet life. And with this sentence, I conclude my talk. I hope you are not bored of my discussions, and thank you for your attention.
Thank you very much, Giovanni, for this very nice presentation.
A few questions.
Thank you. First of all, thank you very much to bring to us all this information, which is essential. I mean, I cannot agree more with you. So first, a comment that maybe you don't know that a few years ago we started a project in Brazil of an ICRANet Brazilian Science Data Center, where we started to construct tools, or to develop the tools for analysis of astrophysical data, maybe the X-rays, gamma rays in the optical, and even where they're putting data from the virtual observatory too, from Swift XRT, from Fermi. And we actually some 3 PhD students working on that at that time. We have a mirror in Pescara of the data center. So we are really working pretty much in that direction. Where not right now because we were slowed down on that specific part, but we really would like very much to continue in this direction.
Allow me to comment. So I knew that. I remember I was here 5 years ago where we had also a couple of talks about that and we discussed. I think that we talked with Remo, and Remo is quite attentive to this because he believes, and I agree with him, he believes that there are a few initiatives like yours. Even in dark matter, there is an initiative of a dark matter data center in Max Planck Munich. There are others. I think that the mission that we have now in the second phase, starting from next year, is that we become really inclusive and encourage all of you, all these initiatives, to be in such a framework, which is the formal framework. And we have an opportunity because being an official and formal framework, this should imply in the next years a discussion about the sustainability of this approach. And we have to work together for our science, for our community.
Absolutely, thank you. But there is a second point. Sorry, Narek, before that, because I think this is important. Because when you looking at your presentation, somewhere where you mentioned the open peer review and all this connection, and was because I was myself working. In Italy, you know, we say a tempo perso, because I don't have very much time on that, but working on an idea of that, but I think we are ready for a proof of concept of that in doing the scholarly publishing system to become, let's say, semi-automatic using blockchain technology.
So I'm telling you the full story. Maybe we should switch off the YouTube now.
Yes.
There are some, okay, the draft of the framework, okay, there are the information confidential for not yet open about the Horizon Europe, but the few lines that I presented in my slide actually correspond to one action. And we are also going to cover this action because of two reasons. One is because it will allow us to continue implementing and deploying and operate the virtual research environment. Secondly, I do not know, but if you have done a sort of brainstorming, I think that we have been, they have been telling to us that in the next months, in the next year, there will be policies top-down and down at CLIs in France and the other Max Planck and other instances. We are going to receive also this influence in order to change, at least to change a little bit, the way we evaluate researchers. It's not sufficient to produce a number of publications. You need to produce your commitment in making fair and accessible your science. Therefore, this is the way, one of the ways through which actions in our community will be funded. So if you have done already the work, or if you have something to propose, I think this is one target, because there will be a dedicated funding. And in my opinion, it's much better that the scientific community anticipate the situation instead of suffering a sort of a top-down position of the rules. We should be always at the center and not run neither after the funding, neither after the policies. We have to be at the center and anticipate the policy. If you have done this work, we should work now.
Yes, definitely.
Okay, yes, thank you for the presentation. Really, it's very interesting, and this open data are really changing everything. But just one question. So you said you make some virtual environment that where we can enter and make analysis and get our results. For example, for CTA, we'll be able to reanalyze the new data, or already published data will be able to.
There are two concepts. First of all, the concept that now as prototype, because are our achievements and we are going to work in the future. You are a scientist, you log in with your ID, with an authentication infrastructure, and you enter in the VRE. So if you have the catalog of software, the catalog data sets, so it depends on your rights. You can have full access or limited access, depending on your identification. You have the workflow, you have the Jupyter notebook to make the workflows. You make your analysis on directly online on the web. You can have access to resources, the computing, the storage. You select your data sets and you publish whatever you do. You can also chart and produce tutorials saying, I have done this and I've reproduced these results with better results compared to the published one. You automatically publish. But from one side, all these legal entities are working together in order to make some economy of scale. We are adopting a certain stack of services for the portal of CTA, SKA, LHC, in order not to reinvent the wheel or going in this disparate way, because the university research agencies are not able to fund it. In the same time, you have also the, and therefore you customize to your specific CTA or whatever observatory. In the same time, the test science project or the open science project, and we are going to be to have funding, important funding on next year about those open science projects, open to all scientists. So we should be ready for that. This is by definition transversal. So you enter in and you propose your project through data, through simulation, and this is a scientific base. It's our community. It's not tuned to one project or another.
I see. I don't know if you know, but ICRANet was involved in some project was called Open Universe.
Yeah.
With our Giovanni and Armenia, Brazil. We were trying to publish everything, and we made a couple of papers. For example, we published all the results observed by Swift. I mean, we just analyzed everything. And last week we had a paper that we produced all the new star spectra for blazars. For example, this is some activity that now is. We are trying to be under the United Nations.
There are background story that can really push ICRANet for in this context.
Exactly.
Or at minimum, Remo wanted I provide you the information in order to make any continuation of your activity in such a context, because this will be the context. It is the context.
Yeah, I agree. In that sense, we have this activity with Open Universe. Still is ongoing now. We have the scripts for analyzing everything.
This should be included.
Yeah, we can easily participate and it will be good for us.
How are the technical tools? How do you deal with the huge amount of data? For example, I'm collaborating now with the group in Japan. They did the simulation, they are trying to analyze the data. There is a very simple problem. The data is 500 gigabytes. And on the other hand, the analysis that we want to do is quite expensive. So we estimate that it will take too much computer resources that they cannot allocate us to do it in their computer. So we have to bring the data to our computer. We have the time, but it's not on our computer. But transferring 500 gigabytes is almost impossible task. And this is just one simulation of two binary Newton standards. So how are you going to, of the kind that you are describing, the theoretician showing, what is your technical solution to analyzing this data? Will you have the computer time allocation to the user, or will you have your own supercomputer resources that will do the data analysis? Or what is the name of the game?
Your question is a manifold question. I try to give three answers. First, 500 gigabyte and the order of magnitude of the computing that you need are not so huge compared to the huge data that we are talking. And so therefore are really in the background and totally, at least in this page of prototype, totally.
Transferring 500 gigabytes
is nothing. No, it's nothing. Secondly, we can guarantee this if we enter in the right speed. The second, but your question is a central question, is that how do you build the sustainable architecture to provide, this is your question, to provide the resources to the Lambda researcher if this Lambda researcher is not neither supported by an agency with its own resources, nor in one of these big collaboration. This is what EOS is going to study and implement. Those are the architecture that they want to implement. The third answer that I can provide to you is that since your scientific target is within our community, and it is our interest, once you are going to have the physicists like the example that you are providing, you are proposing a project, an open science project like yours. We will provide also the resources for the full the full execution of the science project. What we do provide is not computing. What we do provide is that we have the effective services to interface your data with the HPC platform, for instance, that you need, because then after the HPC simulation, you need to transfer your data. This is your question. We need the interface with the data sets and the software, because you want to have the software and to improve the software and to play with workflows. The services are there. The way the economy of providing resources by project has to be explored and put in place by the member states, by the agencies.
Okay, good. Thank you very much. I think we have to move on. Great. So thank you very much again.
Yes,
The next talk will be by Hansjoerg Dittus from the University of Bremen.
Your microphone. Where are these presentation? Your issues. Share. No, but we have to first to share the screen. No, but we have to share the screen first. Sorry. I have to choose here. Why we don't see? Share the screen. This is the share screen, but I don't see the PowerPoint here.
No, it's in the other.
It's in the other as desktop.
No, it's on the other screen.
I'll see. It's another one here. Okay, you have two.
You see?
PowerPoint. I see. Is this a PowerPoint? What is this?
You can do that.
There was. Okay. There is something more. Here. Okay, perfect. That's what we need. Okay.
Now we are ready.
Here we go.
Sorry for the delay. I hope everyone can hear me now. And I'd like to start to keep in time. Let me start with a paper already cited this afternoon. It's the paper of 1971 by Remo Ruffini and John Archibald Wheeler. And for me, it's remarkable because the paper at that time was in some way a new approach. It first of all made black holes and cosmology much more popular than before. There was a big progress in that case, because you see the paper had been published by the European Space Research Organization. I should say the European Space Research Organization was one of the two precursor organizations of the later ESA, founded in 1975. And in 71, we had still two organizations in Europe, one for satellites and science projects, and it was ESRO. And the other one was the ELDO, that was responsible for the launcher program. And because of missing success in the ELDO program, later ESA had been founded in 1975. But for me, it's not only the popularity which had been increased with respect to black holes. And you see the sentence, one of the sentences was a black hole, whether of ordinary size or much larger, provides our laboratory model to gravitational collapse predict the Einstein's theory of the universe itself. So it's a laboratory, but on the other side, and you see it had been published in a larger publication, but the significance of space research, fundamental physics. And fundamental physics didn't become a subject in ESA a long time. And it needed us another 25 years to make it a real subject. And to be honest, in the early 1970s and 1976, and when I started my physics study in the late 70s, cosmology was not well accepted. We had no knowledge about cosmology at that time. And I remember when I was a student that one of my professors said, if you like to go in cosmology lectures, one equation and three free parameters, and whatever you choose for these parameters, you can believe it or not, and it's wrong, completely wrong, or maybe right. So it's like religion. And so it was kicked out of the program. It was not interesting. It was long before we got more information about what is called the microwave background and all that. This came up in the 90s, and until that it was new. So this paper indeed opened predicted is a lot, of course, but it's not shown and never, and it opened the way to use satellites for all what we do today. And whatever we do today, it's based on satellites. We saw these fantastic pictures this morning about X-rays. They're all satellites, and the satellite technology became much, much more important. And the one small side remark: when the Carol's came in, they only changed on the picture. I don't know who. The TV, I don't know why, TV, but they had been modernized a little bit a year later. It's a joke. It's only what I realized, that they, the TV must fall into a black hole. But the idea came later up that we say, okay, in which way we can use space as a laboratory, the more near environment, and not only observing, but maybe also using satellites as probes in the gravitational field, fundamental physics doing with real satellites, not as platforms for telescopes, but maybe using them as probes in the gravitational field itself. And the question was, what are the sensors we have? And I like to point to a paper which had been published 20 years later in 1991. It was titled by Matter Wave Interferometry and Why Quantum Objects Are Fundamental for Establishing a Gravitational Theory. And the authors had been Jürgen Audretsch, Friedrich Hehl, and Klaus Lemmerzahl sitting next to me. And they started an axiomatic approach to space-time geometry. I don't like to go to all this now. I listed it here. That was today we would say, okay, it's exactly what we would expect. The idea was to use, and this is set here, primitive elements. And when we talk about point particles, could be photons, could be protons, whatever, and light rays to measure the structure of space and space-time. And that was in some way a new approach, because now the question was how precisely we can do that. And what I like to report now here is how precisely we can do it now and today. And this is remarkable. And that's what I like to point out here. It started all very early in the late 50s. So Sputnik was the first satellite in 57. And the proposal we're talking here appeared in 1959. It was George Pook, where he proposed to measure the so-called Lense-Tearing precession in the Earth's gravitational field, not using squid-based sensing at that time. They had not been detected, the Josephson effect, that was in 62. But in, let's say, mid of the 60s, it was clear that the only way we have to, or they had, was to detect the so-called London moment, where you have a gyroscope flying on a satellite around the Earth, which is rotating, and then the gyroscope starts precessing in two directions with a device, which is a quantum device, because you use a quantum effect, the tunneling of Cooper electron pairs in a Josephson junction, a superconducting Josephson junction. This was an idea in the mid 60s, and it needed, one has to say that, more than 50 years to realize the experiment. And it was Francis Everest and his group in Stanford, they did it, and they measured this geodetic fact, the geodetic precession, with roughly a 7 milliarc seconds a year. And the other one, the frame dragging effect, or the Lense-Tearing precession, was just 40 milliarc seconds per year. 6,000 against 40, yeah. So to measure that, you have to measure in a range of 1 part in 10 to 3 of a milliarc second per year. And to make this clear, if you see a human hair from a distance of 15 kilometers, it's from one edge to the other one, and that's the rotation within 1 year. And this has to be resolved. And they did it, you see it, and on an accuracy of 15%, it was planned to do it better because of some problems on the spacecraft. It was at the end 15%, but it was a great success for the experiment. And it's was a really remarkable experiment in space for gravitational physics. It's a huge satellite filled with some liquid helium and altogether some tons in weight, and you needed a guide star, and then you could fix it, and then you could calibrate the gyroscope with these rotating. There had been other experiments. Gravity probe B was the one, and then this gravity probe A, already in 1976, had been realized an experiment on a ballistic rocket where they flew a hydrogen maser compared with a hydrogen laser on ground, and could verify the gravitational redshift by in the order of let's say 1 part in 10 to 4. And this is was a long time the most precise test of gravitational redshift. And sometimes, well, this is where the unhappy often comes, or in Germany, oft kommt oft. So this is There was a failed launch of two of the European Galileo satellites in 2015. Failed in that case meant that the satellites didn't end up in a circular orbit, but unfortunately, because there was a rocket failure in an elliptical orbit with a perigee of 13,000 kilometers and an apogee of 25,000 kilometers, and on an inclination of roughly 50 degrees. But the difference between perigee and apogee, of course, was a gravitational signal on the clocks on board. And these satellites, all these GNSS satellites, and we're talking about Galileo, we talk about GPS and so on, are carrying at least 4, sometimes more clocks of different types. This was an ideal laboratory we could use to improve the test of the gravitational redshift. And at that time, the expectation was that we could do it much better than at the end. It had been done. So to tell you what happened was that at the end, it was an improvement, I would say a factor of 5 at the end only. So we have been a little bit disappointed. Nevertheless, the expectation, of course, is sometimes better than reality might be. The problem indeed was the clocks. And the clocks are not very stable on all of these satellites, but stable enough to do the best test for gravitational redshift so far. This is not so bad, and you will see later why. These clocks have a stability of 10 to the minus 14, 10 minus 12 that would be the clocks. And when we heard yesterday from Klaus that we have clocks on ground, one on 10 to the minus 19, and we talk about roughly 7 orders of magnitude. They are worse here in space, because space is, of course, a harsh environment. It's not like in a lab. We can do it in all a well-known environment. And so one can be happy that we can do it on that level. But it's good enough, you will see, for a lot of effects we can measure and reason to do more and improve the clocks for the future. Yeah. And that's what I like to talk a little bit. This is the synopsis. There were 2 papers in 2018 publishing this effect I just talked about with these clocks, and so far the best known test of gravitational redshift so far. So I talked about the atomic clocks on board the GNSS systems, and we have to see we have roughly 150, 160 active GNSS satellites in orbit worldwide. And to say that is a huge lab. We have a clock. We have hundreds of clocks, atomic clocks in space, and only use them to navigate our cars, and ships, and the planes. But we could do much more with this. And the problem is they run all on circular orbits. So there is it's not really an effect. Nevertheless, we have different types of clocks in space. And these fleets of satellites are operated by different countries. Navstar GPS is the US system, Galileo the European one, they do the Chinese one, GLONASS the Russian one, and ICRANet is the Indian one, and there will come more and more in the future. And the question is the operation of this kind of satellites for the future the ideal thing? Because these time signals are used more and more as time standards on Earth. All bank transfers worldwide are relying on the clocks on board. This became a unique time standard worldwide, because it's easy. You have a handheld apparatus where you have the exact time in a range of 10 to the minus 12, 10 to the minus 13. This is, for most applications, the best synchronization you can think about. And that's why it became so popular. And that's why Bureau of Standards are now thinking about using this system and improving the clocks on board of the spacecraft to make it more precise. But then we have to think about many other things with respect to time signal transfer to Earth and back, and because this is not easy. We cannot do it with microwaves in the future. It's too imprecise. So the laboratory is in orbit and we have to use it. That's the message I like to give. But there's only one message. Just to tell you what this is, if we talk about relativistic effects on GNSS, they all fly in orbital heights between 20 and 27,000 kilometers, depending on the system. And for a 20,000 kilometer, I think this is Galileo here, an orbit velocity, we have an orbit velocity of roughly 4 kilometers a second. You see this is 1 part in 10 to minus 5 in c, in the light speed. And the time shift from special relativity per day, per 24 hours, is roughly minus 7 microseconds. And the time delay due to gravitational redshift is plus 45 microseconds per 24 hours of the day with respect to the universal time. And this would result in a distance error per day of more than 11 kilometers a day. Of course, you would say you can't navigate your car on this level. That's completely impossible. But that is not a real result, because what we have is this results only if the time from CSAT to 3 satellites is always compared with a ground clock. That's what we never do. We compare the transmitted signal from 4 satellites, and then the relativistic error is completely negligible. Nevertheless, the problem is, that was the beginning of GPS North Star, but the problem was, meanwhile, it's used as a time standard. And this was not foreseen from the early beginning. So this became a problem anyway. So we have to correct the clocks on board. And this is indeed done. You see that the clock correction on satellites is necessary with respect to use GPS or GNSS, Galileo here in Europe as a universal time standard, because special relativity effects are underestimated by roughly 10 to the minus 8%. And the same is an overestimation of the GRT, the gravitational redshift effect in the same order. And so the clocks run with a reduced frequency compared to the original one to correct this error. And so these effects would compensate both in an orbit of 3,000 kilometer height. You fly much higher, because the 3,000 kilometer orbital height cannot be chosen. It's too dangerous there, because we are flying in the middle of the Van Allen belt, and this is the most dangerous place where you can stay around Earth. And so we go higher. We have to go at least 10,000 kilometers high. And the other reason is, if you fly deeper than 20,000, you need too much satellites. This is another problem. So you see the relativistic Doppler effect also can be calculated. This is roughly 5 kilohertz at a signal frequency of 1.5 gigahertz. We talk about microwaves links, and then you can follow objects with an accuracy in a range of 1 meter per second. That's the precision you have. If you go faster, then your system could run into problems. And this is sometimes we happen if you go very fast on a highway with your car, system cannot really follow sometimes. But this is usually taken out, because here in Europe we have what is called differential GPS. This is a correction on terrestrial transmitters. They repeat the signal, and this gives us the accuracy, which is, of course, if you only take the satellite signals, not as precise. Nevertheless, it's the worldwide unique time standard. So now the question is, what can we do with respect to the clocks? Can we improve the clocks, and can we improve many other things? So we did it. When I have been in DLR, we started this project, and one of this is called Compasso, where we try to use a new iodine standard. It's much more robust, and this has to be then combined with optical communication systems to overcome microwave systems between the satellites and the ground, and in combination with frequency comms to compare the signals and optical terminals. And then you can do space tests for the system. And this has been done, or now we have it on ground. And you see, if we take these breadboard models of the clocks we like to use in the future, this green line on the right side is going much deeper than for the Allen deviation than we have for all the other clocks in space. And this, in particular, on the short period time, on 10 to 0, 10 to minus, the higher frequencies, this is, of course, very helpful for the satellites. Of course, on the long track, it becomes a little bit more complicated. Nevertheless, they're also better than the usual ones. And this is what we hope for the future, that we can increase the clock precision on board of these satellites by roughly 3 orders of magnitude. This would be a big step forward and could help us a lot. For that, we need frequency comps in space to compare the signals. This is also done meanwhile by using ballistic rockets, where they could fly maybe some minutes, up to 10 minutes in space in microgravity environment or weightlessness environment, where they could be tested successfully meanwhile. And of course, one has to develop optical links. All the satellite operation is based on microwave links so far. And to increase the bandwidth, to exchange clock signals, one needs optical links in the future. And to give you an idea how powerful they are, the present technology enables us to transfer up to 13 terabit a second. This is compared to what we do with microwave links, a factor of 10,000 more. So this is great, and it works. It's tested so far and could be used. These terminals are not as big. They're quite small. And of course, with respect to security, it's always better because the focus can be kept. And there are many other advantages, not only the bandwidth, but the bandwidth we use and have to use for a clock precision. That's for sure. So this is well done. This is the clocks. I think that's the present situation with respect to clocks. But there could be done more with quantum sensors. And this is already mentioned in this paper of 1991, is atom interferometry. Atom interferometry is easy because it's not easy, but it's easy to understand. You have a normal interferometer and you replace the light by matter waves or matter beams, and the mirrors by lasers. So light by matter and matter by light, replace it, and then you can have exactly the same equations. But the only difference is we don't deal with optical wavelengths, we deal with the dipole wavelengths. And then we win theoretically a factor of 10 to 10 in accuracy and precision. And this is the idea of having these interferometers. And there you need a light beam, an atom beam as a source. And it should be a coherent beam. And the coherent beam can only be attained if you use Bose-Einstein condensates as the sources. They have to be produced first, and I come to that in a second. And then we have a lot of advantages if we go into space, because atoms don't fall down as they do in labs on Earth. So the interaction time can be increased by at least 1 to 2 orders of magnitude. This is an increase. Then we have a narrow distribution of atom velocities, large differences in the gravitational potential, and very small external distributions. They can all be depressed. And then we come up with highly precise inertial sensors. They measure, as gyroscopes do, circular velocities, but also, of course, linear velocities and accelerations. That's important. They are phase sensitive, and the sensitivity scales with higher order of t, of the interrogation time t. And we can do intrinsic measurement of the frequency differences. This is a lot of advantages we can use. And as a first step, it was a big deal. We made the first time Bose-Einstein condensates in microgravity, in weightlessness. This happened in 2008, first time. And at that time, we have been able to produce Bose-Einstein condensates consisting of 100 up to 1,000 atoms only at that time, but they existed roughly more than 1 second, which was a factor of 10 longer than in the past. That's the longer interrogation time if you go to weightlessness. The weightlessness had been attained on a drop tower in Bremen for roughly 5 seconds at that time. And this is enough. It's a huge tower. And then we could do that. And within these capsules, we could bring down and shrink down these big apparatus due to chip technology we had developed in the last, let's say, 10 no, 20 years. And this is the possibility. And to give you an idea how this looks like, you see these condensates on different times, time windows taken 50, 100, 500, and 1000 milliseconds. And you see this an elongated quantum object at the end. That was the first experiments. Today, they have roughly 1 million atoms in. That's much better, and the resolution is much better. And of course, what you can do as well is you can take 2 species of atoms. So you can do a quantum test of equivalence principle quite easily. And this is what comes up next. And this is what we like, what DLR and also a lot of universities now like to do, and we like to do on the International Space Station together with NASA. These ultra cold atoms, what we say is a cornerstone of the scientific experiments, which enable us to study the fundamental principles of quantum physics, but also gravitational physics, because we use them as inertial sensors. And this will enable us to do gravitational experiments of never reached accuracy in the Earth's gravitational field. This is something where we can verify gravitational theory on real labs, not in black holes. This is, it's on a small scale, and this is by using this sensor, more and more better and better. And of course, it will also enable us to carry out experiments such as dual species atom interferometry for tests with 2 kinds of atoms, medium and sodium, for example, to study quantum behavior, but also prove fundamental principles of gravitational theory. And I think this is a big progress we have, and to go back and maybe build the bridge between today, Raymond, and these things. I like to cite Moshe Yama or Max Yama in 1954 in a book. It was written and titled "The Problem of Space: The Development of Space Theory," when he told the story of Carl Friedrich Gauss. One has to say Gauss, well known as a mathematician, was geometer and serviced was in for the English crown in Hanover, and Hanover at that time had been British, or we should say England had been Hanover, but it's a question who was first. He wrote. Carl Friedrich Gauss measured a triangle fixed in 3 mountains they're all in northern Germany, the Brocken, Hohe Hagen, and the Inselberg. You find them here on this small window. The length of this triangle are measured to 69, 85, and 107 kilometers. It has rarely to be mentioned that within error bars, Carl Friedrich Gauss, did not discover a deviation from 180 degrees. This is the sum of all angles in the flat triangle and flat geometry. And he drew the conclusion from it that the structure of the true and real space, so far as experience permits, a statement is Euclidean. Of course, that's what is expected, because the precision of measurements had not been in that way. But Gauss already had the idea that space could not be described in 3 dimensions only, but one needs more. And it was a problem for him, just to tell you that. This is the 10 Deutsche Mark bill before the euro came many, many years ago. And there was Gauss on. And on the backside was an instrument he invented. This was a so-called heliotrope. He used this for measurements of fixing high church towers in northern Germany. And you see the network, which was in a small picture showing the network he used at that time to do all these geometric services for his crown, for his king. And it's interesting to see that he thought about measurement and did experiments like that to see the curvature of Earth, and not a flat triangle, but there must be a deviation in these 180 degrees. But nevertheless, he was thinking about how one can do it in the future. And there's a lot of hints that he already had the idea that at the end we need more than 3 dimensions. And that was a little bit a problem, a political problem for him, because he was a professor in Göttingen at that time. And in the beginning of beginning of the 19th century, or at the end of the 18th century, it was a problem to come up with theories far beyond present things, because of many reasons. He was employee of the Crown. But if you like to do new research, you have your PhD students. And he also had one, and this was Bernhard Riemann. And Bernhard Riemann developed what is called Riemann mathematics. And later on, Einstein or Marcel Grossmann taught Einstein. And I think it's a nice thing, but we go now from Gauss to Einstein to Marcel Grossmann and then to Remo. And I think it's a good story. We start with simple things, Euclidean geometry. We have also geometry. We have inertial sensing today. And maybe it's a way to increase our knowledge using inertial sensors in our vicinity and look for effects in our solar system. Because when there is dark matter, why not seeing the dark matter effects also in our solar system? And we haven't found anything so far. Thank you.
Thank you very much, Hansjoerg, for this beautiful presentation. While you were speaking, I called Francis Everett, mentioning your word of him. And this was very nice. Congratulations.
But with your equivalence principle experiment, then perhaps it will be from Galileo to Reno.
Yeah. There could be a lot of connections to this. Other questions?
Do we have a time for one quick question? Perhaps I did not understand exactly what you said, but you mentioned the fact that for GPS and Galileo satellite system and so on, one should take into account redshifts, special relativity and gravity one. And this is what I teach to my students, this 11 kilometers, which is not after 1 day. But then you made a remark that by taking 4 satellites, we can forget about this.
Yeah. You can forget it. The original plan from NASA was not, it was not NASA, it was US Air Force, was not to implement a precise time measurement. It's not necessary.
So what I'm teaching to my students is just for the glory of the
No, it's only if you use the time signal as a standard signal worldwide, synchronized, then it's a problem, of course. Then you need, but to make a navigation, you don't need this information.
So I should tell that.
Because there was always a discussion, and I heard this rumoring all the time, and I couldn't imagine that the Air Force officers forgot to synchronize the clocks, and they say this cannot be. They have a lot of experts, and it's indeed, if you see that it works with the 4 satellites, you can do it without knowing the relativistic effects. That's possible because you transfer this time signal from each of the satellite to your ground apparatus. You never compare the time signal with one clock. You have 4 individual time signals and the 3 position signals, and then you need 4 satellites to do it.
So that means that the US Air Force engineers even knew enough about general relativity, but in fact they were right.
Yeah, they were not thinking about to use the funny story of GPS was it was invented to control submarines. If they come up, they should have a direct connection and find their position within minutes. And there was NAFSA at the beginning. They needed roughly 10 minutes, 5 to 10 minutes, but that was too long after a while. for other satellites. And so they like to be shorter. And now they come on only with the antenna out of the water, then they get a signal and they immediately go back down and high speed. That's the strategic advantage. But then you only need the precision, not the time. The time is completely unimportant in that case. But this case came later because we need to detect that it's much easier. We have to time directly on screens. And so why not using that for bank transfers worldwide? All the power networks are working with these satellites today. So that's why the Pro standards become more and more interesting. They said, okay, that's much easier than we did in the past. They have to transfer the signals as well along communication lines between Boulder and Braunschweig and Paris and where all those standards are. And the question is now, could we use this system as a unique time standard as well in the future? But then the clocks have to be much better.
Okay, I think we have to stop here now because, so we thank Hansjoerg again. And in principle, there should be now a ceremony from Pescara. I don't know what this is technically possible. I received a message from Bob Jensen that there in Pescara is no text support, but no technical support, but we will see. So there should be an address by the mayor of Pescara, by Carlo Masci, and this is all coordinated by Costantino Sigismondi.
Yes, now I ask Robert to come.
Okay, so please stay tuned and we will see what will happen in a few minutes. And then we have a short coffee break and then we have the other two talks. One should be happened until now, but we have too much delay due to change of the computers here. And so then we yeah. So
yes, because one we postponed it after the talk because we will run out of the time. It's supposed to be now, but
yeah.
Yes.
Alors, ça me sonne là. Qu'est-ce que c'est qui est débranché? Tout y est? Oh, on va changer celui-là. And we are speaking from ICRANet Secretariat in Pescara, and Professor Costantino Sigismondi connect and
No?
ICRANet ist auch doppelt oder dreifach so.
hello, can you hear us?
Can you hear? Yes, we hear you. We are speaking from ICRANet Secretariat.
Yes, we can, Elisabetta.
Can you hear us?
Yes, we can.
Okay, Professor Costantino Sigismondi is ready to start his intervention and our system manager is helping him to connect, but we are still waiting for the arrival of...
Elisabetta, can you hear us?
Hello?
Yes, we can hear you.
Okay, I was telling you that Professor Costantino Sigismondi is ready to connect on internet, and the mayor of Pescara, we are still waiting for his arrival, but someone rang at the door, so maybe my colleague is opening to him. He's not still arrived, so we are going to connect with Professor Costantino Sigismondi for the moment, and we try to call the mayor to see how long it will take for him to arrive here in ICRANet, in Pescara.
Costantino, vedi di...
Sta collegando, professore Gabriele lo sta finendo di collegare.
Sì.
Buongiorno.
Buongiorno Costantino.
Buongiorno da noi e da tutti i ragazzi che sono qui in sala.
Vedi se arriva il sindaco. Bene, se no fai una ventina di minuti perché abbiamo un programma molto intenso.
Professore, io ieri ho già detto in italiano più o meno il significato di questo luogo, che ho avuto l'onore di vedere nascere dalla sua mente prima, dalle mani sue e dell'architetto Serafini e di tutti i collaboratori del sindaco.
No, but you have to speak in English.
Okay.
But not too long, because we have some 20-25 minutes.
Yes, even less. But the strange thing is that I have to speak about something that I have seen with my eyes.
Good.
During the last 25 years at least, but even with an extra 10 years, because I had the possibility to read an interview that journalists made to you in the book called C'era una volta in Abruzzo. Vabbè. The mayor will arrive at 5:25, so in this 10 minutes I will speak about that and interacting with you possibly.
Good, very good.
And afterwards we will proceed with this ceremony. And so 2 words about Pescara. In Pescara we did a parallel meeting, and this is the joint part with the meeting in Gnss to celebrate your birthday, your 80th birthday.
Thank you.
Yesterday we had Jai Pasakov, the principal expert in solar eclipses in the United States. He is also like your age. He was graduated with Donald Menzel, so the most prominent expert in solar physics in the United States now. And he gave to us a lecture on the science about solar eclipses, while I spoke about lunar eclipses, because yesterday we had a lunar eclipse. We could observe the first phase of this eclipse, while in America they observed the whole duration of the eclipse.
Monsieur, de nouveau des problèmes avec l'appareil. Il n'y a qu'une pile.
It's okay.
Yeah, the study about come faccio a far vedere il mio schermo qua, condividere solo questo? Wow. Okay, this is the image of the sunrise tomorrow. I want to show other images. We are studying with the students of Pescara, Galileo Galilei, Lyceum, and also some students from Roma, the refraction of the at 0.8, so the refraction at the horizon. The celestial body most suitable for doing this study is the sun, because we can see the first light of the sun, while for the moon it's more difficult. And Pescara, coordinating center of ICRANet, of ICRA, of International Center of Relativistic Astrophysics, has been taught by you, by Professor Ruffini, more than 30 years ago. I am sure about that because I read the book C'era una volta in Abruzzo, published around 1984. And in this interview, you spoke about Abruzzo like a big university campus. This big university campus should be linked by a center located in a critical position, and this position was selected as Pescara. And the choice of transforming the oldest train station of Pescara into a coordinating center of theoretical studies in relativistic astrophysics was your idea. I have seen the birth of this idea in the mind, reading this book, without knowing you in person, because I was still at Lyceum at that time. You came in my Lyceum in 1987 doing a lecture on expanding universe, throwing the keys in the eye. You remember this lecture because you had a friend there, so you came to Morgagni Lyceum doing this lecture. And afterwards, I met you in the university as student, as a graduate, and as a graduate student, I took the PhD in theoretical physics with you. During this time, I completed this PhD in 1998. The center of Pescara, this station, was realized, was transformed into this beautiful building and this beautiful room in which we are. The mirror, please, if you have the spec. In this beautiful room that some years ago has been dedicated to the mayor, the former mayor of Pescara, the late Carlo Pace, that I had the honor to meet with you several times in the beginning of 2000 and the end of 1990s. For you and for the people who are attending this meeting, through this device, you can see the audience here and the room with the splendid architecture of early 1900, very, very elegantly preserved and colored by the architect Carlo Serafini. Coordinating center means coordinating minds, coordinating locations. So the station is ideally a coordinating center, and the researchers that are here in the audience as well are the mind to be coordinated. And so this is the idea of ICRANet. Coordinating minds was also the role played by Marin Mersenne in 16th century. He coordinated all the scientists in Europe through letters to assess the discoveries, theoretical and experimental, that all the scientists in Europe sent to him. So with Professor Ruffini and with the aegis of International Astronomical Union, ICRANet, the department dedicated to school, the school department of ICRANet, invented and created the Mersenne Prize, which is a prize to be given to the students, young students of high school, who are able to make some coordinating action between them during the experiment, during the presentation of the experiment. So here we have, for example, Aurora degli Roscioli, who helped us to present better the single experiment with a special format of a single page of PowerPoint. She was very effective to do that, and we used her PowerPoint, her model, for many, many, many occasions, and we will continue to do that. And the same thing is for the students are present here close to me, that are Diego Guglielmi and Daniele Spalletti, that worked again on the networking between the students in laboratory, and also they are here and they had some experience in the experiment that they did. For example, the one that I presented today about the refraction at the horizon with the sun, sunset for Ostia, and sunrise for Pescara. So ideally, we did a meeting, a coordination, a networking between Tyrrhenian Sea, Rome area, and even Civitavecchia, because we had several collaborations in the past years of alternanza scuola-lavoro, alternanza scuola-ricerca, and the Adriatic side of Italy at the level of high school. We have here also Professor Tiziana Pompa and Professor Paola Corona that are there in the audience, and they gave to me this mirror, but also they invented the formula of this year, joining the two seas, Adriatic and Tyrrhenian Sea. And their students are doing this work this year, and for the best works, for the best actions, you can be awarded by the Mersenne Prize 2023. So please go ahead and do it. I show some other images that I presented today. This is the sunrise from Nave di Cascella in Pescara. They are photo. We have also video. Questa finestra fuori, non so come farla fuori. And Professor, if you have some remark on what I said, you are more than welcome. I can repeat that our international guest, Professor Pasakov, formulated by written and by words and by voice his best wishes for your birthday. We also give to you these wishes.
Thank you, Costantino, and thank you for these beautiful pictures on the Adriatic, on the sunrise, and especially for your continuous activity from observing phenomena directly in the universe. It's a small part of the universe, but very significant, because you do that with very young students, which they are very strongly motivated by you. And I think very many of them, they will become astronomers or scientists. And anyway, they will respect more attentively our nature. And I thank you very much for this presentation, for your good idea to bring all these young people in contact with us. And maybe we should wait still a few minutes if the mayor show up, but also tell that you asked me one day to buy a small telescope, and you went up on the roof, you made an observation, and you discover a new star, a new object in the sky. And since then, our center, thanks to you, when you discover a new object in the sky, it becomes an observatory. Can you remind us of this experience? And of course, since we are waiting a few minutes, tell about your splendid work of Betelgeuse done from Pescara, that you managed to understand the role of the Betelgeuse and be in contact with the largest observatory in the world, leading the research on that topic. Maybe a few words on this.
Yes, thanks for remembering these things. I stressed an aspect of the research activity, which can be said in English, boots on the ground, go in the middle of the things, put the hands on. This is the invitation that I did coming here to Pescara, not to see only the tour of Italy of bicycle or the beauty of the sea or the sunrise, but waking up at 4 all the morning to observe, to measure. So I said, go to do this because you will understand much more. About the star you mentioned in 1999, when you bought the telescope, we observed from the roof the Nova Velorum 1999 and Nova Aquile, which was 11 magnitudes, so very, very faint. In Pescara, sky light polluted, it is very difficult to observe that, but we communicate this observation to the American Association of Variable Star Observers, and they gave to us the award you mentioned, the observatory. On this same line, 20 years later, in 2020, on January 17, students are here attending. They attended this meeting. They already graduated from their lyceum, but they are here in this occasion. I already mentioned Aurora, and there is also her friend. Please remember to me the name. And Roberta. We observed, I remember very well, on the same top of the roof, the luminosity of Betelgeuse that night. Betelgeuse, a supergiant in Orion, underwent a very deep minimum, exactly in the correct time, but with a diminution of the luminosity never observed in the last 40, 50 years. So all the people in the world was saying that Betelgeuse was undergoing a supernova explosion. But I said, no, we cannot permit people to say this, because a supernova explosion is a free fall of the nucleus, and it happens in 3 hours, in 2 hours, not in 3 months. So we have to make clarification on that with the expertise of ICRANet people and connecting all the astronomers in the world. So on that occasion, we did it, and we repeated. You invited me to chair a special session of the Marcel-Grossman 16 meeting, the one online of 2021, in which the same and more experts contributed to clarify again the situation of this supergiant star. And now, after 2 years from this event, the situation is still controversial, because Betelgeuse is oscillating with a period which is different from the main periods, the 2 main periods, one of 320 days and another one, 14 months, and another one of nearly 6 years. There is an oscillation of like 6 months, which is now ongoing, that we are trying to understand what is. We received some contribution interesting in Marcel-Grossman 16, but the most interesting things in this case are the data. If you observe the star, you know probably more than if you read the news on that star without observing. And now, in these days, Betelgeuse is emerging, is entering in the rays of the sun. So the way to observe Betelgeuse becomes very complicated. You have to use the infrared observations in daytime. Like in Rome, it was done in the meridian line of Santa Maria degli Angeli with the telescope aiming at a star during the day. So I think I have recalled the astronomical part of what you mentioned. The last thing I can say is about the solar eclipses and solar diameter. It is an activity that I do since 1999. After the total eclipse of Germany, of Europe, we observed on the spot in Germany, taking the car the day before and going there in 10 hours and staying there waiting from the clouds going away and observing. And why the solar diameter and general relativity? because in the university you worked since 1967, Professor Robert Dick tried to assess the influence of solar oblateness to the anomalous precession of Mercury, explained by Einstein with general relativity. The oblateness of the sun is very complicated to be measured. Dicke did it, but after 50 years, the definitive solution is not yet resolved. It is one of the most complicated measurements that are made because the sun is behind the atmosphere, and the turbulence of the atmosphere makes complications in this measurement. So one of the methods is the solar eclipses. That's why yesterday we had Jai Pasachov in this Congress. Other methods are based on space telescopes, but all these methods it's the optical problems of the instruments, because the accuracy needed for state the solar influence to the climate needs an accuracy of less than 10 kilometers on the whole 1.5 million kilometers solar diameter. So 1 part over a million of accuracy. Even if I can do such a measurement in the lab, an accuracy of 1 part over 10 to the 6 is
always
incredibly complicated.
Yes. Do you have any news if the mayor is going to arrive, or ask the secretary maybe?
Yes, they are waiting. They said he is arriving, let's say, not physically yet here. When he arrives, we can say he is here. Otherwise, it's like the experiments. If you don't have the sun up, it is not yet up.
And
there is a refraction effect of the mayor. Yes. Actually, we saw him today because the Tour of Italy we were just behind him when the tour started the tappa from Pescara to Iesi. They probably are arriving now because it's 5 hours ago. So we saw all the rose dressing of the people celebrating also this particular event, because Abruzzo is fibrillating.
Okay, eventually, let's plan when he comes. We can interrupt a few minutes because we have to go on with our program.
Yes, we will call you through the secretary, through the system manager, and
yes, we connect again.
Yeah,
and
this is the right way to do. So I think we move further because we are really very late today.
Yes, we move further, and let's say in 1 hour we could reconnect. Or 45 minutes, 45 minutes. Okay,
yes.
You let us know. Okay.
Otherwise,
yes, as soon as we proceed with Carlos, as the mayor arrives, we interrupt for a moment. Carlos.
Okay. Let's
no
go.
Problem.
Okay, let's go. Congratulations again, and thank you for this present to me, like many other presents you have done. Okay.
Thank you very much.
Thank you. Chiudiamo, Costantino. Orga.
So is Carlos around?
Costantino, you can follow the lecture of Carlo.
Oh, here is. Here you are, Carlos. So,
yes,
sorry
I'm
for
here.
the delay, Carlos. Sorry. Thanks for your questions.
No problem. Can you hear me?
Yes.
Well.
Now is the you can so may I give to Carlos green light to proceed, so you can share your screen.
Yes. So can you see my screen?
Yes, it's okay. So go ahead, please. Thank you.
Great. Great. So, okay, thank you. And first, I would like to, of course, wish warm greetings to Remo and a happy birthday in his day. And I would like also to say a few words about my experience with ICRANet and with Remo in these last years. So I just want to say it was a unique experience to have learned and continue learning fundamental physics and astrophysics with Remo and the people there in ICRANet. And I think, in my opinion, one of the biggest legacies of Remo, besides the huge contribution in science, is that he always pursued the idea that physics is a very important matter to do. And as he always liked to say, you must first have to understand the physics before just jump into the mathematics. So I think this is a nice message that I always like to remember. Okay, so I will start. My talk is about the dark matter at all halo scales, from galaxy center to the entire halo. This presentation is a collaboration with the different people of ICRANet, together with Remo, Jorge, Andreas, and also different people from Argentina, including students of mine, as Martin, Valentina, sorry, and Santiago. Okay, let's start about dark matter halo formation in the realm of collisionless relaxation and coarse-grained entropy maximum. So probably you recognize the equation here on the left, which is the Boltzmann equation coupled to gravity. So this equation tells you the evolution of the phase space density, also as a function of time. And this is the basic equation in which the n-body simulation approach deals to work with the structure formation in the universe. So, but this equation can also be worked out independently or alternatively from the n-body code, cosmological code, and is to work at coarse grain level. So to take a coarse graining of this equation, so you decompose your distribution function into a coarse grain plus fluctuations, and you end up with a equation which resembles Boltzmann equation, but in the right hand side you have a diffusion current with a derivative in terms of velocity only. This equation is kind of, you are building a kinetic theory of in presence of gravity for the evolution of the coarse grain phase space density, and the challenge here is to find the most likely coarse grain phase space density at relaxation. This is possible through a maximum entropy production principle, in which you ask the entropy rate to be maximum, and in which you can demonstrate that at a constant diffusion rate, you can find stationary coarse grain phase space density, which is of the Fermi-Dirac type, as you recognize here in the denominator, with a cutoff in energy in the numerator. This stationary solution of Fermi-Dirac includes effect of evaporation, because for energy, particle energies above the escape energy, you have no more particles. And this is a generalization of the Lynden-Bell theory of violent relaxation. So interestingly, this theory was extended because it was first created for stars under zero gravity, but then was extended for indistinguishable particles such as neutrinos, and in this work, and in the case of neutrinos, the maximum accessible value of the phase space density is proportional to the particle mass force over Planck h cubed. Now, it is possible to build halos at equilibrium, starting from this coarse-grained phase-space density. And the first important concept here is that fermions under self-gravity do admit a perfect fluid approximation. This was demonstrated in this paper of Ruffini and Bonassola by solving explicitly the Einstein-Dirac equation. And therefore, it is possible to work with the Thorman-Oppenheimer-Volkoff equation in general relativity for this gas of fermions of finite temperature. Therefore, you start with this phase-space density I showed in the previous slide here, Fermi-Dirac type, and you build the equation of a state in terms of density and pressure. This is a 4 free parameter theory, which has the particle mass, the temperature, degeneracy parameters in terms of chemical potential over temperature, and the cutoff parameter. You therefore write down the first two, or the Einstein equations, the only two relevant Einstein equations here in spherical symmetry, TOB and mass equation, and then you have the zero and first law of thermodynamics in general relativity, so Tolman and Klein equations, together with energy conservation. Therefore, you have the full system of equations to be solved in order to try to find this equilibrium system of dark matter fermions, that we will like to interpret as dark matter, as you will see. This is a boundary condition problem, as you have to solve for different parameters, such as beta at the center, which is the temperature, the effective temperature of the gas, the degeneracy at the center, theta 0, which we will consider positive in order to consider the Pauli principle, and the cutoff energy at the center. So this system of boundary condition can be solved in a problem in agreement with Halo observables, which is you ask the solution that at a typical Halo scale of 10 to the 4 parsec or tens of kiloparsec and 10 to 11 solar masses, the solution to fulfill with these values, which is more or less here, as you see, where the three profiles matches. So this solution, in this solution, you can see that from outer to central region, that solution is first described by Boltzmann and Boltzmann statistics, where the fermions are in the dilute regime, and there towards the center, the degeneracy is always increasing monotonically until you find this very dense and degenerate core of fermions, which in which you have this continuous transition from classical statistics to quantum statistics, in which you can demonstrate that for degeneracy parameters larger than 10, it is fulfill the quantum conditions in the sense that the thermal de Broglie wavelength is larger than the interparticle mean distance in the core. Interestingly, this is a new family of solution that can be interpreted as dark matter because the profiles, as you see, match the EINASTO or the standard NFW on Halo scales. But interestingly, with the fact that the profiles now depends on the particle mass. So one of the obvious question that one may ask from this solution is, which is the role of the central core at the center of this profile? And so we ask if this is possible to apply to the Milky Way in order to be an alternative or a compact object with similar compacity of the black hole paradigm. So as you see, there is a family of solutions in which you, to solve this boundary condition problem, in which the Halo region it satisfies the rotation curve, as you see in the picture on the right, which is the circular velocity of stars in the Milky Way. The red curve are the best fit to all the data going from outer halo to bulge scales, in which you have this effective rotation curve, because there you have also a streaming motion. But this is, therefore, you can, as you see, you have in the central region is governed by baryons, while in the outer regions you have the halo, the dark matter halo of fermions arising when it is needed to answer for the flatness of the rotation curve here. But most importantly, in the center, this distribution is dominated by dark matter, and you can fulfill these stars are the 8 best resolved S stars in which you can have different families of compact cores of dark matter, which can answer for the dynamics of these stars. Importantly, the particle masses here are constrained from roughly 50 kilo-electron-volt over c squared up to 350 kilo-electron-volt. The maximum mass is because the compact core will undergo a core collapse towards a black hole, while the minimum mass is constrained because otherwise the central core start to overshoot for low the rotation curve for low enough masses. So now this has been up to now until the last years that we have been publishing these results, but we can do better. One can take the data of the S2 star, which has been collected in the more than 20 years already, which led also to the Nobel Prize in Physics in 2020 to the German team and the American team for the discovery of the supermassive compact object at the center of our galaxy. And in this paper, we have recently shown that there is a family of these dark matter core halo solutions in which for particle masses, here you see in the red curve of 56 kilo-electron-volt, the central core can answer for the geodesics of the S2 star in these 1.5 cycle of data, but also for larger particle masses, this is another example of roughly 60 keV, 58. The core is the larger the particle mass, the more compact is the core, and so for 58 keV, you have already prograde precession for the S2 star in compatibility with the Schwarzschild black hole prediction. While for lower particle masses, you may have retrograde precession, but in any case fulfilling with the astrometric data of this S2 star. We have said in this paper that waiting until the next apocenter passage of S2 star in 2026, roughly, it will be possible with the actual accuracy of the observation of BLT to distinguish between one or other trend for the precession of the S2 star. We have extended this analysis for in addition to S2, to the 17 best resolved S stars orbiting Sagittarius A star. And you can see here a best fit in which in dashed you have the Schwarzschild black hole prediction of roughly 4.1 10 to the 6 solar masses, and the reduced chi-square for this astrometric data in which both models, even the rare and the black hole, are comparable. Sorry, here there is a typo here, should read black hole, and the top down should read Schwarzschild, rare model. And but the important point here is that both models are comparable in reduced chi-square, while fitting all these 17 stars. Of course, now we have the latest result on EHT a few days ago. So one important question is, how does this model stand with the recent EHT results? As you know, the EHT analysis support an image which is dominated by a bright, thick ring of roughly 52 microarc seconds, coinciding with a possible solution of Kerr black hole in general relativity, in which by making thousands of different simulations with the magnetohydrodynamical general relativistic simulation with accretion disks, it is possible to roughly match a solution of a black hole with this image, which is the observation here. But regarding coming back a little bit to our model of dark matter, there is this important question to be answered, which is, does any fermion core is compact enough to deflect light in a similar fashion than the black hole? Interestingly, the answer is yes. For example, the solution I have shown here the close to critical solutions, this one, have a radii of the core of this solution. Of course, this dark matter is transparent, but it has a definition of a core. The solution just prior to core collapse has a maximal light deflection, which occurs at 5 gravitational radii. This is a very interesting value because, as you see here, the diameter of this image of this thick ring observed is the diameter is 10 angular gravitational radii divided by the distance of the source. So we just a radii of 5 gravitational radii. So this is important because so configuration which are compact enough, though without an horizon yet, can deflect light and produce a shadow as well. This is a result we have working on from a general relativistic ray tracing code called Skylight, developed by Pelle, Raúl and collaborators. And it is interesting that for example, for this is a basic example done for an alpha disks, so not yet as the fully ADAF accretion disk, which are the more realistic for our galaxy, but for a standard alpha disk or circulation area of standard disk. And just to give an example that with a ray tracing code onto this very compact cores of dark matter, you can have considerable light deflection in order to create this image around the central object, similarly as a black hole. Of course, this is as edge-on view, while as this is an edge view example, while our observation of the galactic center now is roughly face-on. So this is just to say that this is of interest, yet in the future do more study that we are pursuing now of how to form image around these highly compact fermion cores, not yet collapsed. Okay, I will move fast to universality of these fermionic profiles. So we have applied this family of core halo dark matter profiles to other galaxy types, from dwarfs, spiral to ellipticals, from this data you see here on the right. And it's interesting that by asking the model to fulfill with specific radius and mass at a given halo scaling, for example, in dwarf, you have to fulfill with a radius of roughly half kiloparsec and a mass of 10 to 7 solar masses. So this is a very small dwarf spheroidal. And you have a prediction for all the possible core masses. As you can see here in the plot of the top left, the core masses, which are in the y-axis, goes roughly from 10 to 3 up to 10 to 6 solar masses, with therefore providing a natural alternative to intermediate mass black holes. Then moving to spirals, you have another prediction for a family of density profiles with core masses, which now goes from roughly 10 to 5 up to 10 to 8 solar masses, and similarly in ellipticals. Therefore, by making a full coverage of the free parameters, you can have a full family of solutions which make prediction about the central dark matter core concentration alternative to black holes. But one can go even further and say go back to the idea of collapse, right? Because as you know, every model of self-gravitating fermions in general relativity under a perfect fluid will have a critical mass. And this can be, for example, evidenced through the so-called turning point criterion, which tells you that there will be a certain density, threshold density, above which the core mass reaches its maximum. This is the last stable solution. To the right, there are theorems showing that all the solutions to the right are unstable. And therefore, for this typical example that we choose here of 50 keV, when dark matter cores exceed this Oppenheimer bulk of mass, the degeneracy pressure can no longer support its own weight and undergo a core collapse to a supermassive black hole from dark matter. In this case, the masses at which you collapse are roughly 10 to 8 solar masses, for this example, and interestingly may provide initial seeds for formation of supermassive black hole in active galaxies already in the early universe, because this corresponds to think that these halos are born in the early universe. And we recall the previous talk of Felix Mirabel, in which in the early universe you have the seeds of dark matter start to clamp into the dark matter, pristine dark matter halos. But the fact that from this model, this halo can born in a core halo configuration, eventually the central core may collapse, and therefore you may have a seed of supermassive black hole prior star formation. And this may be an interesting, therefore, channel for supermassive black hole formation in the early universe. Finally, I will stop by a few slides about the stellar streams. We have now attacking the problem of
risolviamo il problema della privacy mettendo le mascherine ai ragazzi. Così. Sì.
Okay, so just we'll continue. We have the stellar.
Ragazzi, accogliamo il sindaco di Pescara, l'avvocato Carlo Masci, con grandissimo piacere.
Okay. I will stop if you want to continue later.
È un piacere non solo dei cittadini pescaresi che sono qui presenti, ma anche di alcuni cittadini romani che hanno avuto il piacere di incontrarla lì a Roma, e siamo veramente onorati. Io in particolare perché conosco la tradizione che lega il centro ICRANet alla città di Pescara e al sindaco in particolare. Qui abbiamo la foto di Carlo Pace, che ho avuto l'onore di conoscere durante queste operazioni, in cui questa vecchia stazione è stata trasformata ancora in una stazione, ma di menti che si mettono in connessione in tutto il mondo. E in questa occasione l'abbiamo invitata per premiare le giovanissime menti, perché l'ICRANet si rivolge anche agli studenti come ente internazionale di ricerca nell'astrofisica relativistica, si volge ai giovani per introdurre i giovani al concetto della ricerca. Quindi tramite un'attività che secondo i dettami del governo Renzi si chiamò alternanza scuola-lavoro, noi l'abbiamo declinata in alternanza scuola-ricerca, perché la ricerca è un lavoro che qualifica anche la città di Pescara, e quindi non solo sono presenti qui degli studenti ma sono dalla scuola secondaria, ma sono presenti anche i ricercatori che lavorano qui all'ICRANet e tutto lo staff che sta dietro l'ICRANet. Adesso le nostre segretarie ci portano anche i diplomi del premio Mersenne. Mersenne era uno scienziato dei padri minimi che lavorava a Parigi nel 600 e che tramite la sua corrispondenza è riuscito a mettere in network tutti i ricercatori dell'epoca. Noi pensiamo che nel 600, nel passato, era tutto più lento. Non è vero, la gente era in connessione tale e quale come oggi. C'erano altri mezzi, c'era forse più vivacità, più attenzione, e quindi abbiamo pensato di fare questo premio per i giovani, riportandoci a quest'idea, e i giovani tra loro fanno network, fanno lavoro, fanno ricerca, si spalleggiano a vicenda. Ecco, questo è un po' il risultato.
Carlo, ti ringraziamo molto. Carlo,
ecco, il professor Ruffini sta dicendo qualcosa, ma abbiamo il volume basso, lo alziamo adesso.
Ti ringraziamo molto per essere venuto. Al momento siamo qua a Nizza e stiamo parlando in parallelo con il professor Argüelles dall'Argentina. Quindi che dobbiamo riprendere anche la sua presentazione, la potrete seguire perché è interessantissima sul centro della nostra galassia. E quindi io ringrazio te molto di essere venuto fate le premiazioni velocemente, perché Carlo Argüelles è nel sud del pianeta e sta aspettando di concludere. A te un grazie e ringraziamento di essere venuto per questo festeggiamento dei miei 80 anni.
Professore, buon pomeriggio. Io sono molto onorato di essere qui e vengo all'ICRANet con grande piacere, almeno per 3 motivi. Il primo è che posso darle gli auguri per i suoi 80 anni portati benissimo e continueremo a festeggiarli qui all'ICRANet i prossimi compleanni. Il secondo è perché incontro i giovani, e mi fa veramente piacere, soprattutto giovani che fanno ricerca e che quindi aprono le loro menti. E noi abbiamo bisogno di giovani intraprendenti, giovani che sappiano e vogliano osare e abbiano sguardi originali per guardare lontano. Poi il terzo motivo è che io sono molto legato all'ICRANet, perché quando l'ICRANet ha ottenuto il riconoscimento dall'UNESCO, io ero a Parigi e allora ero un giovane assessore del comune di Pescara che il sindaco Carlo Pace, che è stato un mio padre politico, che è stato un sindaco eccezionale, mai troppo compianto, mi mandò a Parigi insieme al professor Ruffini proprio per acquisire questo dato fondamentale affinché questo spazio diventasse uno spazio che aveva questo riconoscimento dell'UNESCO e quindi diventava territorio franco. In questa struttura abbiamo ospitato scienziati di tutto il mondo, grazie al professor Ruffini, scienziati che hanno segnato il percorso della nostra terra con le loro ricerche. Io ho conosciuto Fang, che era lo scienziato di Piazza Tiananmen. Infatti, quindi abbiamo veramente portato a Pescara qualcosa che introduce Pescara in un network mondiale e che dà peso alla nostra città. E quindi io mi auguro che in futuro ci possano essere ragazzi come voi o voi stessi che possiate venire qui a fare ricerca effettiva attraverso le vostre capacità. Quindi veramente sono orgoglioso di potervi consegnare questo premio dedicato a un matematico che veramente è stato il fulcro di una capacità di ricerca scientifica e di unione di menti incredibili. Poi non si è occupato solo di matematica, ma si è occupato di tutto: filosofia, scienza, musica, no? Perché l'armonia musicale che guida il nostro mondo in qualche modo ha rappresentato anche il suo percorso. Quindi ragazzi, io vi faccio i migliori auguri, vi auguro anche buone vacanze, perché comunque adesso arriveranno le vacanze estive e potrete riposarvi e vivere la nostra città, che è bellissima. Oggi abbiamo avuto il Giro d'Italia, le immagini sono state meravigliose. Quindi grazie per quello che fate, grazie al professor Ruffini, auguri al professor Ruffini.
Grazie molte.
Sono a disposizione per consegnare questi riconoscimenti a tutti voi.
Allora, i riconoscimenti li consegniamo in presenza, questi 4, ma idealmente anche a coloro che non sono potuti venire, perché le edizioni precedenti non sono state svolte per ragioni ovvie. Quindi questi 4 abbiamo la fortuna di averli qui in sala, la fortuna e il piacere di averli qui in sala.
Allora, Daniele Spalletti. Eccomi. Complimenti. Dove sto? Diego Guglielmi. Roberta Chiacchiaretta.
Bene.
Aurora Belli Roceli.
Benissimo, molte grazie. Noi continuiamo e state a sentire qualche parola del centro galattico.
I nomi di questi qua. Sì, sì.
Va bene?
Grazie professore.
Rimanete qualche minuto a sentire le bellissime cose che sentiremo dall'Argentina, da Carlo Argüelles. Grazie ancora Carlo.
Grazie professore. Ecco, gli altri premi, questa è l'edizione, tutte le edizioni precedenti non sono state premiate fisicamente per le ragioni che tutti sapete, quindi
però li citiamo.
li citiamo.
Ricolleghiamo Carlos, per favore.
We can continue with Carlos. Carlos,
Yes.
Carlos, can you
yes, hello.
share your screen again? And
yes, sure, I will.
This was a very important point you were making. Okay?
Yes, so let me go to the last slide. So we ran from central galaxy phenomenology with the S stars, and then also EHT data of light rays being curved around the central object, and with the black hole shadow, and the shadow also around this very compact cores, universality of dark matter profiles, supermassive black hole formation scenario from this dark matter core collapse. And now I would like to conclude with a recent work we are starting here in collaboration with Argentinian students, PhD students, and colleagues about the stellar streams. So, as you know, stellar streams are debris from the pool of the gravitational of the bulk of the galaxy within the caused by the galaxy, the bulk of the galaxy to the satellites as globular clusters or dwarf spheroidal. So they are excellent tracers to the gravitational potential of the Milky Way, which are independent, for example, of the, as you know, rotation curve tracers obtained from the H1 data. So you have here more than 40 stellar streams comprising by the Gaia ED-R3 release. And we will center here on a cold stream, which is the Gd1 stream, which is the debris left by a globular cluster along a short coverage in the sky. Here you have the cold stream traveling through the halo in self-coordinates. This is from the work of Price, Whelan, and Bonaca. These coordinates are angular coordinates, are roughly coordinates along the stream, either along the stream and perpendicular to it. And this work has been recognized all the stars from the stream with respect to the background stars, and also in agreement with the color diagram and the proper motion analysis of the globular cluster in order to recognize all the stars that belong to this cluster. And so we want to test these dark matter fermion halos with these streams if the observables of this Gd1 stream can be explained by a Milky Way composed by baryons and fermions. So we start with the Gd1 observables. The observables are the location in the sky, Phi1 and Phi2, also the heliocentric velocity of a star along the stream, which is this best fit in the blue curve in the bottom left panel. And then in this middle panel, you have the proper motions in right ascension and declination. And finally, also photometric distance in kiloparsecs. You can see that the typical distance of this cold stream, stellar stream, are roughly 10, 12 kiloparsec. So it's interesting. This is a very interesting radial coverage for our galaxy, because in regards of our dark matter fermionic profiles, it stands in the middle of the galaxy roughly. So we as I showed before, we started from the below milliparsec and roughly to scales typically of even horizon scales, then to the middle scales of this 12 kiloparsec, and a rotation curve which ends roughly at the border of our galaxy at roughly 50 kiloparsec. So if we can answer for these independent tracers in the middle of our galaxy and answer for this motion with this dark matter halo model, it will be an interesting probe for this kind of model. So the stream finder have 800 roughly candidates for this stream. But making a cross correlation with spectroscopy, you end up with roughly 160 stars in radial velocity sample. And then we take these observables and make this full model of the galaxy potential plus the Gd1 stream. So the galaxy potential, we consider the fermionic rare model with the 2 free parameters, plus the baryons, which are fixed by the literature. And in the rare model, because this rare model is a model with 4 free parameters, we fix the particle mass and central temperature in order for the central core to be in agreement with the S stars around Sagittarius A star. Therefore, we end up with a model of a full model of 2 free parameters for our model plus 6 free parameters of initial condition of the orbit of the Gd1 stream. Interestingly, we find best fit parameters that you can see here, the fit, the best fit we did with a genetic algorithm of this rare equation. And they are very good fit with quite low chi-square, roughly about 32, which is comparable with the state-of-the-art best fit done by Ibata et al. With a slightly oblate NFW profile for the dark matter halos. Therefore, this is a nice result we have achieved recently, and also in overall good agreement with the independent rotation curve tracer. Therefore, now we have covered these different scales in which this dark matter fermion can distribute from the very center to intermediate regions to the outer halo. And I leave you here with the conclusions. So accounting for the quantum nature of the dark matter in the relaxation of halos can lead to a novel dark matter profiles, which can develop a dense and compact nucleus surrounded by a diluted halo. These core halo profiles can explain galactic rotation curves while providing an alternative to central black holes. Typically, for fermion masses from 55 up to 380, the dense core can explain precise astrometric data of S stars, and likely you have to go to close to critical solutions or maybe collapse, but we will have to wait for next data to match EHT results. And finally, importantly, these fermionic profiles allow for gravitational collapse of the dark matter core into a supermassive black hole, and therefore this may provide a novel supermassive black hole mechanism from dark matter in the early universe. Thank you very much, and I open for questions.
Thank you very much, Carlos. And,
thank you.
Let me ask you a question, if I can.
Yes.
The problem is, of course, these latest results that they were published in the few days ago, we were aware of this sort of emission, which is in arcs. But I think from our consideration, it is extremely hard to infer from these arcs, at least from what we have seen, any information about the black hole parameters, since, of course, they don't follow geodesics. Therefore, we cannot follow a geodesic path. Therefore, I'm very curious to see the results of the computation.
Yes, yes, I think this is important comment because it's true the resolution of EHT up to now is not enough to resolve, for example, the photon sphere, right? The close to the event horizon in the black hole paradigm, there is the ISCO, the innermost stable circular orbit of photons, and these photons they can circularize many times, creating this pattern of light which is cannot be resolved until now. So,
no, I'm sorry. Here is a conceptual point. The point is not a question of resolving. The point that is crucial to understand if they are not only, if they are really geodesics. In the sense, it's not a technical point. It is possible that all these paths don't join in a geodesic, and therefore not only, but we have evidence from what I've heard that they are arch without the possibility to follow geodesics. In other words, they are changing in time the geodesics, and this is very serious. Okay,
yes.
we'll see.
Yes. Yes, by the way, the hotspots, yes, I think you mean the hotspots. It's true that the hotspots, it has been shown that these very bright hotspots in several gravitational radius respect to the center are shown not to be fully geodesics, are pattern motion due to magnetic fields and so on. Exactly. This is true. This is true. This is true. And for in these hotspots are like that because there are many different papers saying this. And but then we have also the light rays also staying there. So one has to from ray tracing you can try to solve these null geodesics, how to bend around the central object in besides these hotspots, which are of more probably of more complex nature. Yeah.
Well, we have to keep watching.
Yeah.
Okay. Thank you. And let's see if there is any other comment.
Thank you. Thank you, Carlos.
Okay. Thank you.
So we should move.
So, yeah, thank you. Then
Klaus, good.
Yeah, we see Brian.
Okay. So we're going to me now?
Sì. Sì.
Window screen, select screen or what?
Va bene. Cosa è successo?
Let's see if I get this to start.
Cosa è successo, per favore? Quelli della luce, del telefono.
Okay, I want to do entire screen. Okay, let's see, allow.
Okay, can I share this? Won't share. Okay. So let's see, is my screen being shared at all? So you can hear me, right?
Yes, we hear you, but we don't see your screen.
Okay, so can you see my face?
No, not even your face.
Can't see my face. Cannot unlock the share video. Okay, not allowing me to do it. Share screen. My screen's not showing either. Okay, that's just what I was worried about. Still not showing? Let's see if I have some kind of protocol that's set up that's blocking this from happening.
You could open your file and then go to Zoom and then the green button and then you can.
Okay, slow down.
Program is shown up, which you have opened.
Okay,
and then go to the
beginning again. I was actually trying to troubleshoot, so please start from the beginning. So you want me to, oh, what was the first step? My Zoom is on, so we can start from there. No one wants to help me. Someone was giving me instructions a second ago. Okay, not going to get any help. Okay.
So Brian, did you open already your presentation in your PC? So after that, yes, you go to the green button, sharing your screen, and then show up. There is a pop-up of Zoom that show you the different screens on your computer, and you just pick up the screen you would like to share.
Okay, I hit share screen again. Am I, okay, let's close this down. No, that's not going to work. Okay, so I'm going to go in through my own Zoom and see what I can do here. You don't want to do that or do? This is what I was worried about in doing this. I haven't done one of these before. I've never presented on Zoom.
But you are using a Mac?
We'll make it work because I put a lot of time into this. Okay, so
is your PC is a Mac? Is Mac PC?
I'm using a PC. Oh,
is a Mac? Is a Mac?
Is that on now? You see it now?
No.
Really? You are, it's because I'm screen sharing. Okay. And let's see. Sharing, not working. Screen is paused.
So I will share mine so I can show you.
Okay, hang on a second. Let me go. And so one of the things is I open this through my browser. I don't know if that's a problem or not. But I also have my Zoom open.
Do you see my screen now?
Okay, I have nothing that looks like that in my Zoom. Okay, which is typical of Zoom. I noticed that all the examples, all the screens they show look different than the ones that I have. I downloaded the latest version. You're in Adobe Acrobat, it looks like right now.
Oh, Brian,
Adobe. Yeah.
Brian, let's see this. Can you send to me, send by email your PDF?
That's not gonna work. You do that with somebody else and none of the slides got fixed. No. If I can't get it to work, I'm just not going to do it. It's just, I've tried hard. I did my best. There are other things in life here. So so right now I'm in my browser. Are you saying I do not want to hit share screen when I'm in my browser? Should I close my browser? I couldn't join from my Zoom connection because it wanted a passcode. I didn't have a passcode. I just had a link.
Brian, but if you like, Brian, send me the file. Send me the PDF file by email.
I'm not going to do it that way. I'm not going to do it. It's going to be just garbage. It's too hard to do it this way. Because I need to control the slides. I need to point to things on the slides. I'm not going to be able to do it. Okay. And it won't be done properly, and I don't want to do it not properly. It's just not worth it. So I'm going to try a new share. Try it again. And I'm going to hit my I'll just hit the main screen, I guess.
If it's not working out, then it cannot out.
Still nothing there.
I think
I don't think I'm logged in properly.
one basic solution is to send the file to Jorge. It's not what we want to have, but it would be a solution to get the information you want to transfer to us. If you don't want that, then I think you should.
Yeah, well, I think you should move on. I tried hard. I studied Zoom for about 3 hours this week.
It could somehow work with the Zoom. And
can we?
So I can hear you, and I'm listening to everybody through my browser. It's a Firefox browser, and I can see my picture. My Zoom is open. My camera's working. You can see my picture, and that's all I know. I also know that
we see only your name. We don't see. You don't see.
Well, one of my problems is I can't. This thing says start video. I can't make it. Okay, so this looks like it's select a speaker. Let's see. I can't do the start video. I think I need to hit this, get the start video to not have a red line. It won't go. Is there any way I can log in with a passcode? Can you guys email me a passcode so I can log in?
What is
it? Or is that?
Let's ask Gabriele if he can do something. Gabriele. Okay.
Well, at least I get to share a new experience with you, Remo. They're not always good, but.
So the protocol for the talk is to open the file that you want to present, then go to a Zoom,
let's do like that.
Then you can share the screen.
Okay. You keep trying.
You may send the file to Jorge, and then he can show us the file.
You keep trying, and if it does not work, we can try tomorrow night at the same time.
And I think, you know what? It just isn't my thing. I just don't. Resume share. Keep trying this. Anything now showing up? I guess I'm not sharing my screen with anyone. I'm in something. I'm just going to log out and I'll log back in.
Okay.
And what happens if I can't log back in, so be it, and we'll just leave it at that. Okay.
Otherwise, tomorrow at the same time.
No, I'm not going to do it tomorrow. I'm done. I'm done. This is enough for me. I tried, Remo. I love you.
Same for me. Thank you anyway. Thank you anyway. And of course, we have done so many things together. And your work is so enormously important. And we really want to hear that. Therefore, let's try to find a way. Eventually.
Professor Ruffini, Professor Ruffini, happy birthday to you. Yeah, here is Wenbin from University of South China.
Yes.
Yeah, I also send me your email. I made a happy birthday card for you.
Okay, thank you so much, Wenbin. Look forward
happy
to
birthday.
Bye.
Yeah.
Okay, I go out a moment. Let's see if you can solve. I have here Pascal Chardonnay and Giovanni Lamanna, who are with me, and I need to speak to them a moment. Okay, let's see if you can solve. I will keep watching.
No, if yes, I think
we should now close the session. perhaps we can find a solution tomorrow also, or then to another occasion to see this paper or the presentation of Brian Punsly. Does everybody agree with that? Okay, then I would close this afternoon session. This was ich gehe jetzt raus.
Unmute. Is this working at all? Can anyone hear me here? Jeez.
I can see you very well now. It's a progress, definitely. I can see you with the blue shirt, and it works very beautifully. Yes, I can hear you.
Wow, okay. I just had to log out for something happened. All I know is Firefox wanted to update, and I think that could have been a lot of it. As soon as I closed it, said, can we update? I said, okay, fine. So I'm going to see if we can share my screen before I talk a little bit. So the actual, can you see my actual, can you see my presentation in the background here on the right?
Very well, very well.
Yay, 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 yay. Okay, fine. I'm going to see if we can share my screen, right? Talk a little bit. So the actual.
Also Bob Johnson coming in. No, it's okay.
Okay. I saw Robert. What did Robert say?
Very well, very well.
Yay, 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 yay. Okay. I'm going to see if we can share my screen, right?
Don't forget.
So the actual.
Also Bob Johnson coming in.
A lot of people were talking at once, and a lot of people weren't using headsets with microphones like me, so there's a lot of reverberation there, so I didn't catch any of that. By the way, Carlos was very clear. So one person I could hear perfectly. Thank you for that. Okay, so you can see my presentation, obviously, right? Okay, I'm going to assume you still can. And I just wanted to start off by saying I'm glad to be in this, being included in this honoring of Remo. Knowing him was very fortunate for me, and it's changed my life a lot. I started following Remo's work when I started studying astrophysical jets from black holes in the mid to late 80s. And I realized a lot of the fundamental papers that were written on particles and fields and charges close to black holes, like half of them. One night in the late 90s, I got a call at 3 in the morning, and it's Remo, and he's interested in my paper on Kerr-Newman black holes and gamma rays. And I was saying, this is great. This is the expert on the subject, on the physics, and he thinks it's interesting. So he made me feel important in a time in my life when the rest of the world wasn't. And I'm very grateful to him. And it's really quite an honor to celebrate this. So I'm going to go to my presentation now. I'm going to go to full screen, assuming it's still working. Go to slideshow. Okay, there we, oops, and it went an extra. So how do I get rid of this thing? That over there to the side. So I was working on the theory of these astrophysical jets, and it became clear after a while that debating the theory in the literature was not really the way to go. With the advent of the funding of the Event Horizon Telescope, it became clear that the testing ground for these different theories was going to be the jet in M87. And so that's the purpose of these studies I've been doing for the last 5 years, to try to use the observations that we have, some very good observations, to try to figure out what actually is the jet in M87. And that will determine what's the right solution. So now this isn't working. I'll just escape. No, escape isn't working. Oh my God. Okay. I know what's going on here. This is, God damn. Sorry. I got to, let's go and minus this, go to services. I think I'm getting a Windows update while I'm doing this, and my computer's running like crazy and it's locked up. This is nuts. Stop that. Hopefully this will fix everything. Jeez. This keeps getting better and better. Okay. So there we go. So I'm going to go in this mode. It's a little safer, so I can actually see what's going on. I'm going to actually minimize this and make sure that you guys are still around. I had Windows trying to update while I'm doing this. This computer actually is a good computer when it's working, and I can thank Remo for this. Okay, so that's good. Okay, by the way, since my whole system locked up and I've been having trouble, can someone verify that you can still hear me and see my screen?
We hear you.
Okay, because my hard drive's going like 1,000,000 miles a second trying to turn this Windows update off now. This makes it more interesting. It adds drama to hopefully not a too dry of a topic here. In my toolbar, let's try this again. Yay, I'm unlocked. Okay, I can actually change the slides. So getting back to the science here, and thank you, Robert, for chiming in for sanity check. The Event Horizon Telescope is just basically very long baseline interferometry at a very high frequency, 230 gigahertz. And the data is extremely complicated to understand. It's patchy data, and it's now been conflated with a library of numerical simulations. And so they're almost like testing both at the same time. The this premise of a black hole and the simulations that produce the jet that they like. And we're actually going to compare these simulated jets that's in their library of over 60,000 simulations to what M87 actually is. We want to point out here real quickly that no jet's been detected yet. And so we really want to know what are the near field properties of the jet that constrain any viable jet that EHT might actually find. And can their numerical models reproduce this? So I'm going to use these two magnificent VLBI images that we have, one at 43 gigahertz and one at 86 gigahertz. So they don't have as much resolution as the EHT. And I'm going to be able to constrain a lot of the jet structure between 85 M and 550 M, where M's the geometrized mass of the black hole. And this is even after deprojection. A typical angle of line of sight is 18 degrees. That's one I use, but talk about that a little bit more later. And just to put this in perspective, the EHT analyst has a diameter of about 12 M of emission. So it's from 7 times the EHT analyst size to maybe 35 times. We're going to be looking in that range. Can't get closer. So there are very few constraints on a viable jet model above the EHT analyst now. And the reason is we don't know even the most basic things about the jets. That's in the current epoch. We don't know its power, we don't know its particle composition, and its density. And we don't know the transverse structure of the jet. At least it's not, some of this has been published, but it's not publicized or well understood. So I'm going to determine these from this, from the observations. So currently, the astronomical community uses terms like sheath and spine to describe jets. And this is based on things that they learned on parsec and tens of parsec scales, trying to understand them. But it's not even know if this is relevant or what the dimensions would be or how prominent this should be on sub-light year scales like we're going to be talking about. And the main thing that you see is that this notion of a sheath that's so morphable as for theorists is really misleading. The only detectable emission from the M87 jet, very close to the black hole, is this thick-walled, tubular proton-electron jet, because it's collimated, and it contains at least 50% of the total jet volume. And that's even assuming that the invisible interior is part of the jet. There may actually be nothing there. We don't know, because you can't see it. So when I talk about this invisible interior, you'll see it in the image coming up, I think the next slide. And this tubular jet, I didn't have the approximately greater than or equal symbol, is slightly bigger than 10 to the 42 ergs per second of power, and transports 10 to the -4 solar masses per year of protonic material. It's also at the epoch of observation. Of course, at other epochs, when you look at low resolution, you might see like it's a million years ago or 1,000 years ago. The power could be very different. You don't know what the accretion state was then. So it's also mildly relativistic. You see here, it's about a quarter of the speed of light to maybe 0.38, going from 350 M to 650 M. So I'm making all these strong claims, but I have very good evidence, as we'll see, to show that these things are almost certainly true. And the most prominent jet feature, it's 300 and 550 MOA, where we can really see resolve the jet well, is this extreme limb brightening. And this is a very powerful, difficult to understand concept with lots of information in it. And what I'm going to show in this talk is that when you take the synthetic images from the simulations, 60,000 of them used by the EHT collaboration, they're actually center brightened, not edge or limb brightened in the same region. And this region in the literature has been claimed to be very well represented by the jets. And they're proving that the simulations are great. And so this is this huge disconnect with observation. And so here's the best image ever made. And so VLBI is very difficult, especially at high frequency. It's very imperfect because you have very few stations and it's mainly just open space between them. And you're trying to make this one large aperture. And very smart astronomers designed very difficult experiments to try to capture this. But there's so many variables at play. There's the troposphere variations and corrections that you have to make. There's weather. Stations go out. They go out intermittently. And Craig Walker studied this for more than a decade. He'd look at it all the time with 43 gigahertz VLBA, and he is a fantastic radio astronomer. And sure enough, one time in one of his most aggressive experiments, everything worked perfectly, even better than he thought it would. And this is the image. And so what's so special about the image? Why am I glowing over this thing? It's kind of ugly looking. This is the only image of M87 ever created where you can see the counterjet. Sometimes there's a little blob here, but the counterjet has the exact same morphology as the jet. And this, the way I created this image was I just said, you know what? I don't care about the region we can't resolve. It's just this weird shaped blob. I'm going to pick the contour. So I'm looking at the weaker resolved portions of the jet and just saturate this because it's of no interest. And so it's this image is my starting point for the study. And I'm going to look in this range over here. The first thing you notice is that the counterjet, besides having the same very similar morphology as the jet, it has these two ridges and there's this trough of nothing in the middle. This is the center of the interior that's not observed. Another thing that's kind of surprised me is that the ratio in the surface brightness on the counterjet side and the jet side is only like a factor of 5 or 10. So this is not highly relativistic. And so that's the first thing I determined. I said, well, how fast is this thing going? And is it actually well defined? So I looked at, so the approaching jet's Doppler enhanced, and the receding jet is, so this is Doppler enhanced, and that's why it's brighter, and the receding jet is Doppler deboosted. And so we have all they're very simple formulas for this. And the 18 degrees is based on people's discussions of flares and this bright optical spot HST1. So, and it's always, everyone always picks a number between like 17 and 19. But it's not going to depend a lot on that. But it's definitely fairly polar. Why is this an important thing to calculate? So before this, people were mainly relying on component motions. So they see a faint component moving, but they make some kind of statement about the speed, and no one else was actually using the counterjet. So, but these are patterns in a bulk flow. They don't represent the bulk flow. They can be shocks that are very much faster than the bulk flow, especially with magnetized shocks. So this is one of the analyses I did. I took this is the jet flux in green, and the counterjet corrected for the fact that it's going away from us and giving it the same boost, Doppler boost as if it were approaching, and assumed bilateral symmetry. And this black line, this black curve, the units are over here. It's just, I just said, I'm just going to pick the simplest thing, uniform acceleration. Of course, I could put tons of degrees of freedom and nail all these spots, perfectly, and the acceleration would go up and down and stuff like that. So you can see it's not that relativistic. So now I knew two pieces of information. I knew because that picture had the flux density at different points in little strips, and I had the jet speed. I said, well, if I assume very standard ideas, conservation of energy, angular momentum, and mass flux, the standard properties of any wind equation, I can probably figure out what this jet is. And that's in this AppJ letter. And so I looked at every possibility: turbulent magnetic fields with protons, turbulent magnetic fields with positrons, ordered magnetic fields with like a Poynting flux with protons and positrons and electrons, so every possibility, and different lepton cutoffs, but there was only one solution, which is very fortunate. It had to be protonic, and it's the only solution that satisfies the flux density profile, the velocity profile, and the conservation laws of physics, and it's Poynting flux driven. And you can see how the quality of the fit, and considering there are a lot of variabilities in how this thing's working, and the simplicity of the models I made. It's a plus or minus 3 or 4% for mass flux and jet power. And this is just in one direction. So if you want to know the total jet power, you multiply this by 2. If you want to know the total mass flux, you multiply this by 2. And you can see the solution makes total sense as well. The Poynting flux energy is decreasing along this portion of the jets I'm looking at from 0.4 to 0.65 m away from the nucleus. And the kinetic energy, the protons are increasing at the same rate. So it's a conversion of Poynting flux to proton kinetic energy. That's what's accelerating the jet. Angular momentum is also conserved, and it's independent of this field line angular velocity. Any field line angular velocity will give the exact same plot, it turns out, but the units over here change. I just picked this one because it was a provocative anchoring point that I knew the AppJ letter people would like and the HD people. So here's this picture again. And this is the new stuff I'm working on. It took me a long time to understand this. And you can see why when you see the complexities. This limb brightening. And this is just like gloss over. Oh yeah, it's limb brightening. There's something on the edge. It's a sheath, you know, it's a boundary layer. But I started thinking about it. I said, gee, I can't make this thing make any sense. The peak to nadir ratio, here's the peaks of these ridges or rails. And sometimes they're called the double rail profile. And here's the nadir, is 6 to 10. That's actually a lot. And so we have this restoring beam that's kind of, this is full with half maximum, the restoring beam of this image. It's kind of blurring everything, which is kind of a problem. But it took a typical crosscut from this paper. It's a half a milliarc second from the nucleus. And I did a Gaussian fit to this crosscut. Here's the nadir and our two peaks. And so I'm going to show you a lot of these just to get you used to what's going on here. The north is always going to be on the left. And here's a restoring beam, the Gaussian profile, and it's definitely narrower. It's narrower than the peaks. And so I'm thinking, okay, that kind of looks pretty wide, but can I quantify this? And you have to be careful. First, you think it's wide, but it's still comparable in size to the restoring beam. So there's a lot of blurring. So you have to I deconvolve the restoring beam, and I defined like an apparent width, which is the full width, half maximum of these ridges after I've deconvolved the restoring beam. So it's narrower than the picture over that I just showed. And of course, there's no way of knowing how the full width, and that's a point of this whole analysis to follow. There's no way of knowing how the full width half maximum corresponds to a real physical distance. That's just a mathematical statement that's common to use. So I had to define, first I wanted to define a radius so I could quantify how wide is this. So I took the peak to peak separation, and it also is going to include like half of this apparent width on each side. You know, that's the width of the wall. Half of the wall is going to be on the inside, half's on the other side of the peak. So that gives you the R. I had 6 crosscuts in this paper, and so that means 12 ridges. And I got omega W apparent, the width over the radius is 42%, which is huge. So the ridges are really wide. And I'm thinking, wow, this is very strange. Wide ridges next to deep nadirs and limb brightening they're just totally at odds with each other. This is going to be really hard to understand. But the saving grace is I figured I had three very strong constraints, and they're interdependent. You have that define this double rail morphology. You have the rail-to-rail separation, the ridge-to-ridge separation. You have the peak-to-nadir intensity ratio for each rail, and you also have the rail width. So I said, okay, there's hope here that you could figure this out. But there's two huge complications. One is the low resolution. Another one that's really mind-boggling is the line of sight and the flux density gradient. Since it's almost polar, you're looking down the throat of this jet. And so the line of sight enters the jet on the near side as you're going through. And I'll have a 3D picture to show you because I don't even know, if someone explained this to me at the beginning, I wouldn't have followed it. That the line of sight enters at low emissivity, goes through the center of the jet and exits near the black hole at close to the black hole at higher emissivity. And that's a big problem, and we'll see why later. So in order to make progress, I went to higher resolution. This is the best 86 gigahertz image, but you can see this is typical. You don't see anything with the counterjet, it's just a little blob. So I made these crosscuts. So here's the first very provocative graph. So I plotted the crosscuts, and I'm going a little bit ahead, getting ahead of myself. This is the most promising EHT type simulation. Is the dashed line, the crosscuts are the solid lines. So as you start with the physical source, the crosscuts are not resolved, and as you go farther out, you get enough separation, and you actually can see the deep null. Notice that the EHT collaboration simulations peak in the middle. They're exactly the opposite of what they should be. And there's a cheat there, the way they did it. This came from this paper, this Nature Astronomy paper. They were able to give me the FITS files so I could look at this. So they made the nucleus of their simulation much, much brighter than actually M87. And they were comparing the M87 VLBI image and their simulations, the one I showed a few slides up, just to let you know. They were using this same image. And so everything's restored with the same beam. It's an exact trade-off. There's no artifacts of different resolution. So with their synthetic jets, if I normalize the flux to the nucleus flux of M87, so the two nuclei are the same, it's much fainter. The reason why they do this cheat is because of this problem. The jets also fade way too rapidly. So even with the fake, look, it's way down here. And the peak for the red one is over there at 0.6. So I think, well, how can I figure out what the source is? So normally the limb brightening is a phenomenon of planetary nebula and supernova remnants, and you have high resolution in the optical observations, and that you have very narrow ridges in the planetary nebula, and you get this divergence with 1 over the square root of the width of the ridge. But this has no relevance, it turns out. When I read about this stuff, then I realized, hey, this is completely irrelevant. M87 images have low resolution and wide ridges. So in order to explain this, I wanted some simple tools. I wanted to minimize the number of degrees of freedom. Of course, with lots of degrees of freedom, you can describe anything. And the way I looked at it, this is a persistent phenomena. So I should be able to find the primary drivers of the wide ridges and the deep naders with very simple axisymmetric models. They may not be perfect, but I should be able to do it. So I looked at simple sources. I tried a cone. I tried a cylinder first. And so this is the inside of the cylinder is with this brick red color, and the outside is this green. So you can see the width of the wall. This is 25% of the radius. Now these are lines of sight they're white, they're harder to see, but they're going to be easier to see two pictures from here. And these are all the lines of sight that make one of those crosscuts with the two peaks and the nadir. And so the nadir actually comes through here. As you see, it enters at low emissivity and exits at high. And this model doesn't work. I tried the cone with the opening angle that Craig Walker estimated, the intrinsic opening angle. And here we have the lines of sight. Here's the intersection with the wall. Is this a different shade of green over here? And the problem is, when you try to get the deep nadir, is this brightest portion, which I can estimate from the 43 gigahertz image. I already have those flux densities of strips across it. It's not a huge gradient. It's a factor of 2 or maybe a little more. But this is just too bright. Oh, okay, go back. This is too bright. It just ruins your nadir. So I came with a solution. It's called a tapered cone plus cylinder. And it's very, very hard to visualize. But I think this picture I put in the paper because it's also an aid to understand all the geometry going on. You think, oh, cylinders and a plane. I can understand this really well. I couldn't until I drew it in the 3D imaging and started playing around with it. So what it is, if you remember back the image, take my word for it, because I'm not going to go back because I'm going to run long on time. And I'll hopefully show the image again. It's basically cylindrical. It's slight fluctuations from like 0.65 to 0.4 milliarc seconds from the core. So I have a cylinder and then I have a cone at the end that tapers down towards the nucleus. And the thing that makes this work is I taper the cone. It starts at a quarter of the radius out here, and then it's only 5% of the radius when it gets down to the bottom. And that makes this part fainter. So it doesn't dominate the nadir and make the nadir really bright. And that's the key. There was no other geometry that works without the tapering the wall. And this is an example of the longest line of sight. So I got this blow up over here. The longest line of sight where the limb brightening occurs comes in through this area, comes out the other end. So I ran a test. So this is the numerical experiment I did with different types of cones. This is the 43 gigahertz crosscut, the most symmetric one I had. And so I tried the cone, the cylinder, a cylinder with narrower walls, and it got better and better, but I could never get there. I couldn't go any farther with the cylinder idea. And then because of the blurring from the restoring beam. And then with the tapered cylinder, I tried 2 types. And the main thing that matters is getting rid of that emissivity at the exit point. So the cones are very similar. This has a ratio of 5 of the width down to the exit point, and this one's only 3.3, even though it starts with a narrower cone. But this one actually does a little bit better. So this is a pretty decent idea for getting the nadirs, but I'm not really changing the width very much with all this. And so I explored what's going on with the width. Why can't I get it wider? And so I'm trying, this one's 0.35 and 0.1 at the cylinder part of this, the wide part, top of the cone. And not much change because of the blurring of the restoring beam. And as I made it wider and wider, I start to lose my deep nadir. So I'm in the process, if I make it any wider, this isn't going to work. So I had to think of something else. There's something else going on. And so what I did is I realized that if I put another cone around it, a narrow wall cone around it, like a sheath, this is my version of a sheath, it's going to have much larger spacings because the walls of the cylinder are already wide. It's going to have much larger spacing than the interior tubular wall jet. And because the spacing is larger, the restoring beam is not going to seem as big relative to the 2 peaks, and it's going to resolve the actual physics better. It'll get the limb brightening of the ridge and the nadir more defined. and it actually worked out. So here are the two most axisymmetric crosscuts I can make of the 86 gigahertz image. So I have, this is at 0.35 milliarc seconds from the black hole. And you can see the fit's pretty good. The sheath is much fainter. And then I tried one at one of these wide cylinders plus the tapered cone at 0.55 milliarc seconds. It's actually more resolved than the other one. One of the problems with the other one is that it's not fully resolved. And so the nadir doesn't come all the way down. But the jet widens out a little bit. Okay. And so it's more resolved here. So not only is this showing that you get a decent fit, but it also shows that the models I'm using is capturing the difference in the resolutions that you would get with a different jet width relative to the restoring beam size. It's a very strong argument this is on the right point, on the right track. So if I put 0.35 into this formula, I can get the fraction of the jet that's in this tubular wall, and it's 58% without the sheath. It's huge. So I'm thinking this is a remarkable result that the hand waving on the sheath never really thought about, that a lot of people do. So I actually looked, even though super resolution is not formally justified, it's done a lot by radio astronomers, and I have a super resolved version of the 86 gigahertz image. I did the same analysis to try to show that this was not just an artifact of the low resolution, and sure enough, I get the same results. It's at least 58%. So I felt pretty confident. So how does this relate to the EHT simulations? Well, their favorite simulation of the EHT collaboration has a magnetically arrested disk, MAD, to make it cute, and as they call it, it has high spin. And the high spin in these simulations was also shown in this paper to actually decrease the decay rate, so make the jet brighter farther out. So this is the right one to pick. It's their best case, like they say it is. And I made this, I plotted the synthesized image from this type of simulation. It's really obvious it's center bright. I mean, I didn't have to do all the analysis, but if I don't, like in another paper on simulations, like in this one, they say, well, you know, we need a little more edge brightening, you know. It's not exactly perfect, we still need a little more edge brightening, but it's not, that's just so misleading, as you can see from those plots. So what makes this really strange is that the model they use, they set the jet emissivity to 0. Probably most people listening say, what? I thought they were looking at the jet. They set and I'll tell you why. They set the jet emissivity to 0, and they let everything else glow. And the things that glow the most, the external part, right next to the jet, and this is the sheath. And so if you think about it, this is the most edge brightened structure you could ever make. The counterintuitive thing is, but limb brightening in the sky plane is never pronounced in synthetic images. So I looked at their source. This is the source function before convolution with a restoring beam. And I put in the same crosscuts as in this picture right here. And I put it the full width half maximum of the restoring beam at the peak of each one of the crosscuts. And I realized all they're picking up is just local bright spots. And if you look at this source, it's mainly just a bunch of voids with these bright wisps going through. And the problem is they don't have enough emissivity column within each one of these restoring beams. If you have a lot of emissivity within like M87 has within the restoring beam, it makes for a lot of flux in that restoring beam. And so it'll be very bright, and any local bright spot will just be overwhelmed by all the emissivity in the thick wall. So what's ironic is that the fact that the EHT simulations don't work actually corroborates the thick wall tubular jet finding. Because you should never get limb brightening without a thick wall, especially with whole gaps in it. So what are the implications here for the EHT simulations? Well, one thing I didn't bring up, I want to look at everything in tandem, all we know about the interior jet, is something I showed in an earlier paper, that from 85M to 210M, the simulated jets are only half as wide as M87. That's a lot. And these guys confirmed it, but kind of downplayed it. The streamlines clearly need to diverge much more rapidly from the launch site than the simulations have. Then we have the edge brightening from 300M to 550M versus center brightening, and we have this extreme limb brightening and wide ridges that can only be made by a thick wall tubular jet. So where can they go from here? So one, you cannot fix 2 and 3 above by extending the emissivity into the jet, as someone suggested they're going to do after my 2019 paper. Because first of all, it makes number 1 worse and doesn't actually help. And it's not tenable. And this is a little bit to determine why they set the emissivity to 0. Is because if you go farther in than the most aggressive images have done, the jet particles in the jet actually are not physically made. They're from a mass floor numerical diffusion. If you actually let that jet glow, it would be much brighter than the sheath. So they don't have the tools to do it. The other thing is they can't fix the jet by moving the jet emissivity outward, because this is collimated. The jet's collimated. We can see it in the image of M87. There's one collimated outflow that occurs in the simulations. It's this funnel wall jet where the accretion flow rams into the centrifugal barrier near the black hole and makes a thin, wafer-thin ejection up the side of this accretion funnel. And its wafer thin is probably what we're seeing in this, much of the sheath that shows up in their images. There's no disk-driven jet in the images. And the reason why is that if in the simulations, the poloidal magnetic field is very turbulent. And you only see any kind of ordered structure if you average over time in azimuth. And you need the ordered field, an actual ordered field, to magnetically sling the material out to make a magnetic jet out of the disk. And that's why they don't see it. Now, another thing they could do is they could try to entrain 10 to the -4 solar masses per year in the first quarter light year of jet propagation. Now, first of all, this isn't captured by the simulation, but they could inject it somehow. He claimed that you try to inject it. But there would have to be this weird thing. Well, how does it get 1/3 of the way to the distance to the jet center in this short amount of time? And also, it doesn't fix number 1. So this is very non-trivial to resolve, and it's been very downplayed. Of course it has. Let's do a summary here. So the observed tubular jet is the dominant portion of the jet. It's not the subordinate little sheath. It has a moderate Fanaroff-Riley 1 jet power like all low redshift, low luminosity AGN have. 10 to the 42 ergs per second. Very typical. It's on the stronger end, but not the strongest possible FR1 luminosity. And a mass flux, it's actually fairly comparable to the accretion rate estimates of the Event Horizon Telescope collaboration. It could be as like a factor of 10 less, but that's still pretty close. Also, the EHT simulations aren't even close to describing what's observed, and the resolution of this issue is not trivial. And my final comment is that the core of the thick wall tubular jet's not detected, so there's really no constraint on its power or composition from observations. So that's my contribution to the subject over here. So if there are any questions, if anyone's still around.
Fantastic, very beautiful, and follow. And of course, I like very much what you told me also about this other thing about the Galactic Center. You told me I have not seen the data and I cannot say anything. And I think we'll see the data is crazy. It's more crazy than the other one. I think the New York Times and this other picture are just a scandal. And really, we have to make clear, like the other scandal of Thorne for the gravitational waves, which I think we are narrowing down finally, are absolute nonsense. And thank you, because I think you started a very important, very, very, very important new field. And we have started together the extraction of rotational energy from the black hole. And we are going on now with Jorge and with so many people, and with your help, we will do really the theory of M87, and with the dark matter people, the theory of the object in the galactic center and our galactic center. Thank you so much. This was one of the greatest presents you gave me for my 8th day.
I'm glad.
Thank you so much.
Thank you for inviting me, Remo.
Brian, say hello to your wife and your son.
Yeah, my wife says that you have a lot of class, and she really likes you.
And
you're very nice when she came.
Jacopo was here now, listening, and he enjoyed very much. We are
really? That's good.
Very, very strongly, and ad maiora, all my best.
Okay.
But there are many other questions apart mine.
Okay, that makes it fun. We got a lot of questions. We can talk more.
Jorge? It's late. I think it's, let's stop like that, and let's hear each other again soon. Bye.
We're coming back. Are we going to come back later? Or
no, I don't know.
The program says it's over.
Because we were supposed to stop at 6 o'clock, and right now are 7:10, and they have to go to dinner.
Okay.
But
all right. Well,
we have the record of this lecture.
Hi, Remo.
And we will circulate the tape to everyone on YouTube.
Great.
Okay.
Happy birthday.
Thanks again.